About 4.6 billion years ago, something disturbed a cloud. We don't know what. Maybe a nearby supernova shockwave, maybe a collision between gas clouds, maybe just the random pressure fluctuations that happen in interstellar space. But something nudged a region of the solar nebula, that vast cold disk of gas and dust orbiting the proto-sun. And that nudge started everything. The sun hadn't ignited yet. It was just a knot of density, a protostar surrounded by material. And in that disk, gravity was already pulling things together. Dust grains colliding, sticking, forming pebbles, pebbles forming rocks, rocks forming planetesimals, objects maybe a kilometer across, planetesimals forming planetary embryos, each stage collisions releasing heat, energy, reshaping the landscape. This process is called accretion, and it's mechanical, predictable. Gravity does what gravity does. But here's what's important to understand. Even though gravity follows simple rules, the outcome is not predetermined. Small differences in starting conditions, the density of the nebula here versus there, the temperature gradient, random collisions lead to wildly different results. This is what physicists call sensitive dependence on initial conditions, or in simpler terms, contingency. The solar system didn't have to form the way it did. It just did. As the disk settled and cooled, something crucial happened. A line formed, not a visible line, but a boundary. We call it the snow line. Inside this line, closer to the proto-sun, it was hot. Too hot for water, methane, ammonia, carbon dioxide to remain solid. These ices evaporated. They drifted outward, carried by solar wind and radiation pressure, leaving the inner solar system starved of volatile material. Outside the snow line, farther out, it was cold enough for ices to survive. And this changed everything. Because ices are sticky. When you have ice particles in a cold disk, they accumulate rapidly. They're more likely to collide and stick than to bounce apart. It's like the difference between throwing snowballs versus throwing sand. Sand bounces. Snow sticks. So the embryos beyond the snow line grew fast, exponentially fast. Jupiter, Saturn, maybe others we don't see anymore. They grew so massive, so quickly, that they could capture hydrogen and helium directly from the nebula, building thick atmospheres, becoming gas giants. Fundamentally different from anything forming in the inner solar system. And this is where we need to pause. Because this division, this separation between rocky planets and gas giants, shaped everything that would come after. If the snow line hadn't been where it was, if the temperature gradient had been different, if Jupiter had formed slightly differently or slightly later, everything changes. Earth might never have formed. Or if it did, it would be a super-Earth, massive, dense, nothing like the planet we know. Venus might have been the habitable one instead. Mars might have been larger. The solar system we see today, the one that gave rise to life, exists partly because of where that line happened to be. But the story doesn't end there, because Jupiter and Saturn, once they got massive enough, didn't stay in their orbits. They migrated. And when we say migrated, we don't mean they drifted slightly. We mean they moved inward, outward, reshuffling the entire system. This is called the Grand Tack hypothesis, and it's become the leading model for understanding how our solar system actually formed. Here's what likely happened. Jupiter, massive and gravity-dominant, started moving inward, closer to the sun. Maybe all the way to where Mars's orbit is now, or even closer. As it moved, it was a bulldozer, anything in its path. Asteroids, planetesimals, smaller embryos, got either scattered or flung outward or consumed. The inner solar system was being cleared out, reorganized, destroyed, and rebuilt. This is crucial to understand. Without this migration, Earth wouldn't exist in its current form. Jupiter's inward migration disrupted planet formation in the inner solar system. It scattered material. It created a harsher environment. Everything Earth had built up to that point got reshuffled. And then, and this is the critical part, Jupiter reached a point where it couldn't go farther inward. Maybe Saturn's gravity caught it. Maybe the disk's structure changed. Maybe there's a resonance mechanism we still don't fully understand. But Jupiter reversed course. It started migrating outward again. And as it withdrew, it left behind a reorganized system. Asteroids in new orbits, planetesimals distributed differently, a cosmic wreckage. And from that wreckage, Earth formed. Think about that. Earth didn't form in a calm, orderly process. Earth formed in the aftermath of planetary chaos, in a system that had been nearly destroyed and then reshaped. This is not how we used to think about planetary formation. For a long time, we imagined the solar system formed smoothly. Dust accumulated. Planets grew. Everything settled into place. Orderly. Predictable. But the evidence suggests something wilder, something more violent, something that could have easily gone wrong. And we know this because we found other solar systems, thousands of them now, and many of them look nothing like ours. We found massive gas giants orbiting extremely close to their stars. We call them hot Jupiters. According to our old models, these shouldn't exist. Planets that massive can't form that close to a star. There's not enough material. But they exist everywhere we look. So what happened? The same thing that happened to Jupiter. They migrated inward. But in many of these systems, something went wrong. They got stuck close to their star, or they migrated in chaotic ways, or their orbits got tilted and misaligned. We also see systems with planets that orbit backwards, retrograde orbits. We see systems crowded with debris. We see systems that look broken, unstable, like they're still recovering from planetary collisions. And then we look at our solar system, and it looks gentle by comparison, orderly, stable, which raises a question. Why did our solar system get lucky? Why did Jupiter's migration work out? Why didn't we end up with a hot Jupiter orbiting where Mercury is? And the honest answer is, we don't fully know. Contingency, chance, a specific sequence of events that could have gone differently. But the chaos wasn't over, because around 50 million years after the solar system began forming, so roughly 4.55 billion years ago, something catastrophic happened. A Mars-sized object collided with the proto-Earth. We call it Theia from Greek mythology. But the name is less important than what it did. This wasn't a glancing blow. It wasn't a merger between two roughly equal-sized objects. This was a catastrophic impact. High-speed collision. Violent. The collision was so intense that it partially vaporized both objects. It ejected an enormous amount of material into orbit around what remained of Earth. Material torn from both the proto-Earth and Theia. And from that debris disk, from the wreckage of two worlds, the Moon formed. This is called the giant impact hypothesis, and it explains a lot. Why the Moon exists. Why Earth has such a large moon relative to its size. Most planets don't have moons this large, it's unusual. Why the moon's composition is so similar to Earth's, but not identical. It has more iron-poor material. consistent with a giant impact scenario. Why Earth's rotation is tilted 23.5 degrees relative to its orbital plane. The impact tilted us. But here's what we need to sit with for a moment. We're not certain the giant impact had to happen. Simulations of planetary formation can produce Earth-like planets without a giant impact. The impact that created our moon was contingent, a chance encounter between two planetary embryos in the chaos of the forming solar system. And if it hadn't happened, Earth would be different. It would likely rotate faster, possibly too fast for a stable climate. The length of our day would be different. Tides would be different. The moon's stabilizing influence on Earth's axial tilt wouldn't exist, which means Earth's climate would be less stable, more prone to wild swings, less hospitable to life. So the existence of the moon, something we take for granted, was the result of a cosmic accident, a collision that nearly destroyed Earth, but instead created the conditions for life to eventually emerge. Think about the irony of that. And the debris from that collision settled eventually into the moon, which then began to slowly move away from Earth, a process that continues today. The moon moves away from us at about 3.8 centimeters per year. But while the moon was settling, something else was happening. The solar system was still full of leftover material, asteroids, comets, planetesimals that hadn't been incorporated into planets or flung into space, and these were still dangerous. For roughly the first 500 million years of the solar system's existence, a period we call the Late Heavy Bombardment, or the Great Bombardment, the inner planets were under constant assault, impacts constantly, craters covering every surface, heat from impacts, outgassing, vaporization. This wasn't gentle. This wasn't a thin rain of small meteorites. This was bombardment. But here's where the story gets interesting. Because this bombardment, violent as it was, might have delivered the materials necessary for life. See, when the solar system first formed, water and organic compounds were scarce in the inner solar system. They were frozen, beyond the snowline, inaccessible to the inner planets. Earth was born dry. The inner solar system was a desert. But asteroids and comets, which formed in those colder outer regions, carried water, carbon, nitrogen, complex organic molecules. And during the bombardment, they delivered these materials to the inner planets, impact after impact, bringing water, bringing carbon, bringing the building blocks of life. Slowly, over millions of years, Earth was being enriched, watered, chemically primed, and by the time the bombardment ended, around 3.8 billion years ago, Earth had oceans, actual liquid water oceans. It had an atmosphere. It had the chemical diversity necessary for biology. And here's where the story becomes even stranger. Because very soon after the bombardment ended, almost suspiciously soon, life appeared. We have evidence of life on Earth dating back at least 3.7 billion years, maybe further, possibly as far back as 4.1 billion years, though that's debated, which means life emerged during or immediately after the heavy bombardment, when impacts were still happening, when the surface was still hostile, when the world was still being reshaped by chaos. How did life manage that? Think about what that means. Imagine a world where large meteorites impact regularly. Heat from impacts is intense, localized. Impacts vaporize rock, create shock waves, trigger earthquakes and volcanic eruptions. The atmosphere is probably toxic. Ammonia, methane, CO2, nitrogen. No ozone layer yet. No protection from UV radiation. The ocean is warming from the constant bombardment. The surface is a wasteland. And yet, somewhere in this hellscape, life began. One possibility: deep underground or deep underwater, life was sheltered from the worst of the bombardment. The subsurface would have been more stable, more protected. Hydrothermal vents, cracks in the ocean floor where hot, mineral-rich water flows, could have provided both energy and chemistry. A safe haven, a place where the laws of chemistry could operate without constant interruption. Another possibility: life didn't just emerge once, it emerged multiple times and got wiped out multiple times by impacts, by radiation, by chemical changes, until eventually one lineage survived, thrived, spread. Or maybe the bombardment wasn't as severe as we thought. Impacts still happened, but perhaps not as frequently or as intensely as older models suggested. Maybe there were windows, periods of relative calm, where life could gain a foothold. Or maybe all three are true. The truth is, we don't fully know, but what we do know is this: life didn't wait for the world to become safe. It didn't wait for the bombardment to end. It emerged during chaos. It took root in hell. And that tells us something profound about life itself, that it's not fragile, or rather, it is fragile, but it's also tenacious. It finds a way, even in conditions that seem impossible. And by 3.5 billion years ago, life was established enough to leave chemical signatures in the rocks. By 2.4 billion years ago, life had transformed Earth's atmosphere, filling it with oxygen, a waste product of photosynthesis. Life didn't just survive on early Earth, it changed Earth, shaped it, made it something new. So now we have a forming solar system. Jupiter and Saturn have migrated and reshuffled the disk. The inner planets have accreted from planetesimals in chaos. Earth has suffered a giant impact and gained a moon. The bombardment has ended. Life has emerged and is beginning to flourish. And then, something remarkable happened. The system stabilized. After all that chaos, after all that disruption, the solar system settled into a configuration that has remained largely stable for the past 3.8 billion years. And that's genuinely surprising, because dynamical systems, systems with multiple interacting bodies under gravity, tend to be chaotic. In chaos theory, small changes in initial conditions lead to wildly different outcomes over time. The butterfly effect. A butterfly flapping its wings in Brazil causes a tornado in Texas. Yet our solar system has maintained its structure. The planets haven't collided. They haven't been ejected. They haven't spiraled into the sun. Why? Part of it is that the planets are far enough apart that gravitational interactions are relatively gentle. They nudge each other slightly, but not catastrophically. Part of it might be that the current configuration is in some kind of quasi-stable state. Not perfectly stable, nothing in a chaotic system truly is, but stable enough. The orbits resonate with each other in ways that dampen perturbations rather than amplifying them. And part of it is luck, or contingency. We happen to end up in a state that persisted. But here's an unsettling thought. We don't know for certain that this stability will last forever. There are models, serious models from respected astrophysicists, suggesting that on timescales of trillions of years, the orbits of the inner planets might become chaotic. One of them might be ejected, might collide with another, might spiral into the sun, which means even though our solar system seems permanent to us, billions of years old, billions to go on truly cosmic timescales, it's temporary, fragile, contingent. Everything falls apart eventually. But not yet, not for billions of years. And we're here to ask the question, Why is our solar system stable while so many others aren't? When we started finding exoplanets in the 1990s, we discovered something shocking. Many solar systems look chaotic. Hot Jupiters orbiting close to their stars, planets with wildly eccentric elliptical orbits, planetary systems where the orbital planes are misaligned, planets tilted at odd angles relative to each other in their star, massive debris disks suggesting recent collisions, systems that look broken. And when we compare our solar system to these, ours looks almost arranged, structured, harmonious. The planets orbit in roughly the same plane. Their orbits are nearly circular. They're spaced in a stable configuration. Everything fits together like it was designed. But was it designed or was it luck? The answer might be both and neither. See, there are physical principles at work. Planets tend to end up in roughly coplanar orbits if they form from a disk. Orbits tend to circularize over time due to dynamical friction. The solar system's current state isn't random. It follows from physics. But the specific arrangement, the exact distances, the exact masses, the exact configuration, that's contingent. That's the outcome of a particular history. And here's where observational bias comes in. We can only observe solar systems that exist, and we can only exist in solar systems compatible with our existence. If our solar system were chaotic, if orbits were misaligned, if impacts were frequent and catastrophic, we wouldn't be here to observe it. So when we ask, why is our solar system so stable? Part of the answer is because we're here asking the question. A solar system unstable enough to eject Earth or make it uninhabitable would never produce observers. So we wouldn't see it. We'd only ever observe stable systems, or at least systems stable enough for life to emerge. This is called the anthropic principle, and it's not really an explanation. It's more of a reminder that our perspective is biased. We're looking at the universe from inside it, from a place compatible with our existence. But it's also true, and it matters. Though we should ask, was Earth that lucky, or was there something else going on? Consider Venus. Venus is only slightly smaller than Earth. It's only slightly closer to the Sun. Early on, 4 billion years ago, Venus might have had oceans, might have been habitable. But something went wrong. Or right, depending on your perspective. The Sun was weaker back then. It was fainter in astronomical terms. But Venus is closer to the Sun than Earth, so it received more heat. And as the Sun got slightly brighter over billions of years, Venus heated up more. Water in the atmosphere began to evaporate. Water vapor is a greenhouse gas, so more evaporation meant more heat, which meant more evaporation. A runaway greenhouse effect. Eventually, the atmosphere became so hot that water molecules were broken apart by UV radiation. Hydrogen escaped into space. Venus lost its oceans. Its atmosphere became a hellscape, dense, toxic, hot enough to melt lead. Earth, being slightly farther from the Sun, avoided this fate. We got the Goldilocks distance, not too hot, not too cold. But this wasn't inevitable. If Earth had been slightly closer to the Sun, we might have followed Venus's path. If Earth had been slightly farther, we might have frozen over. We landed in a habitable zone by chance. Or consider Mars. Mars is smaller than Earth. It cooled faster. Its magnetic field shut down. The solar wind stripped away its atmosphere. Mars lost its oceans, became the dry, cold desert we see today. 3 rocky planets, 3 very different fates. And ours, The one that gave rise to life, to consciousness, to us, was the one that happened to work out. That's not destiny. That's contingency. But here's something we haven't fully addressed. We've been talking about the solar system's formation as though it's ancient history. Done and dusted, 4.6 billion years ago. Settled, finished. But that's not quite right. The solar system is still forming, still evolving, still becoming. Asteroids are still being perturbed by planetary gravity. They're still colliding, still migrating to new orbits. The Oort cloud, that vast sphere of comets surrounding the solar system, containing trillions of objects, is still being shaped by passing stars. Sometimes a nearby star will pass close enough to perturb the Oort cloud. Knock loose a comet. Send it toward the inner solar system. And the solar system's outer boundaries is still being defined by gravitational interactions with the rest of the galaxy. The Milky Way's gravity is constantly pulling at us, nudging us, reshaping us. And inside the system, life on Earth continues to evolve, to diversify, to shape its environment. Humans have walked on the moon. We've sent probes to every planet. We've altered Earth's atmosphere and chemistry in ways that will persist for millennia. We've become a geological force. So the solar system isn't a finished product. It's not a museum piece. It's a process, still unfolding, still contingent on interactions both internal and external. And there's a timeline to it all. The sun is a middle-aged star, about halfway through its life. In roughly 5 billion years, it will exhaust its hydrogen fuel. It will expand. It will become a red giant. It will likely engulf Mercury. It will likely engulf Venus. It might engulf Earth. The inner solar system, the place where life emerged, where we evolved, where we built civilizations, will be incinerated. And then the sun will shed its outer layers. It will become a white dwarf, a small, dense, cooling ember. And the remaining planets, whatever's left, will orbit that ember in darkness, growing colder. And eventually, trillions of years from now, the white dwarf will cool completely. It will become a black dwarf, invisible, cold, and the planets will orbit in eternal darkness. The solar system has a lifespan, not infinite, finite. Everything that we see, everything that exists, has a beginning and an end. So let's step back and see the full arc. 4.6 billion years ago, a cloud was disturbed. Gravity began to work. Dust became pebbles. Pebbles became planetesimals. Planetesimals became planets. The snow line divided the system into inner and outer regions. Rocky planets here, gas giants there. Jupiter and Saturn migrated. They reshuffled the entire system. They nearly destroyed the inner solar system. Then they reversed course. From the wreckage, Earth formed. And then Earth was struck by a Mars-sized planet. A catastrophic impact, which nearly destroyed Earth, but created the moon. And then the bombardment came. Asteroids and comets raining down, bringing water, bringing chemistry, bringing the building blocks of life. And in that hell, in that period of chaos and violence, life emerged. Somehow, impossibly, life took root. And then the system stabilized. The bombardment ended. Life spread and diversified. And eventually, billions of years later, that life evolved consciousness. Evolved to the point where it could ask questions about where it came from, about how the solar system formed, about whether any of it was inevitable. And the answer is no, none of it was inevitable. Every step of the way, things could have gone differently. Jupiter could have migrated inward and never come back. The giant impact could have destroyed Earth completely. Life could have never emerged. Venus could have been the habitable planet instead of Earth. Mars could have retained its atmosphere and become the center of life in the solar system. But none of that happened. Instead, this happened. This specific sequence of contingent events, this particular arrangement of matter and energy, this solar system, and we are the product of that history. We are here because of a cloud that was disturbed, because of a snow line in the right place, because Jupiter migrated and then migrated back, because Earth was struck by Theia, because asteroids and comets delivered water and chemistry, because life emerged in hell and survived, because the system stabilized, because billions of years of evolution produced consciousness. We are here because of contingency, because of chance, because the universe rolled the dice and, against absurd odds, the numbers came up in our favor. But there's something else we should consider, something that reframes the entire question. We ask, how did the solar system form? And we look for the mechanisms, the processes, the physics, gravity, accretion, migration, impact. But that's only half the question. The other half is, why does the solar system have the structure it does? And the answer isn't just physics, it's also history, contingency, the accumulated result of countless chance encounters and critical junctures. And here's the thing. If you could rewind time 4.6 billion years, go back to that moment when the cloud was disturbed, and then let everything happen again, starting from slightly different initial conditions, you probably wouldn't get this solar system again. You might get something similar, but not identical. Maybe Jupiter forms in a different location. Maybe the giant impact never happens. Maybe asteroids follow different orbits. Maybe life never emerges. Maybe life emerges on Venus instead of Earth. Maybe humans never evolve. Maybe consciousness never arises in this system at all. The odds of getting exactly this solar system again with all its specific details are vanishingly small, astronomical in the truest sense of the word. Which means our solar system is unique, not in the sense of being cosmically special, but in the sense of being unrepeatable, a one-time outcome of a chaotic process. And that's both humbling and profound. It means our existence is contingent not just on physics, but on history, on a specific sequence of events that could have gone differently. It means we owe our existence to luck, to chance, to the particular way the universe happened to unfold in this corner of the galaxy. And it means the solar system, this arrangement of planets and moons and asteroids and comets, is irreplaceable, precious, not in a sentimental way, but in the sense that it won't happen again. The universe is vast. There are billions of solar systems, trillions probably, if we count exoplanets around distant stars. But there is only one solar system like this one, only one that produced this specific outcome, only one that produced us. And that brings us to something crucial, something that ties back to the very beginning of our question. We are asking, how did the solar system form? But we're asking from inside the solar system. We are asking it because the solar system formed this way. We are not external observers. We are not scientists looking at the solar system from the outside, from some vantage point beyond it all. We are the solar system, in a sense. We are made of stardust. Literally, the carbon in our bodies was forged in the heart of dying stars. The oxygen in our lungs was created in stellar furnaces. The iron in our blood came from supernova explosions. We are not separate from the solar system. We are part of it, a product of its history, an expression of its structure. And the solar system itself is not separate from the larger cosmos. It's a subsystem within the galaxy, which is a subsystem within the universe, which is, well, we don't know what. But the point is, we are nested within layers of systems, connected to everything, shaped by everything. And when we ask, how did the solar system form? We're really asking, how did we come to be? And the answer is through a process of increasing complexity, through gravity pulling together dust, through chemistry building molecules, through life emerging from chemistry, through evolution producing consciousness, through consciousness wondering about its own origins. That's the full story, not just the formation of the solar system, but the formation of the universe gradually over billions of years, from simplicity to complexity, from disorder to order, from non-life to mind. And we are where that process has brought us, at least so far. But the story isn't over. The solar system continues to form. Life on Earth continues to evolve. We, as a species, continue to change. And the future is contingent. It's not predetermined. We face choices about how we treat Earth, about how we treat each other, about whether we explore beyond this planet or remain confined to it, about whether we survive the challenges we've created or whether we destroy ourselves. The solar system's future depends partly on physics, partly on chemistry, partly on biology, but increasingly it depends on us, on human choices, on what we decide to do. We are no longer passive inhabitants of the solar system. We are active participants in its evolution. We are shaping it, and that's both terrifying and remarkable, because it means we have responsibility, but also agency. We can't rewind time 4.6 billion years and try again, but we can choose what happens next. And when we zoom out even further, when we think about the solar system not in isolation, but as part of the cosmos, the contingency deepens. The Milky Way, our galaxy, is on a collision course with Andromeda. In about 4.5 billion years, the two galaxies will merge. This collision might destabilize the solar system, might knock us into a different orbit, might alter our future. Or it might not. We can't be sure. And beyond that, the universe itself is expanding, accelerating actually, driven by something we don't fully understand, dark energy. And if that acceleration continues indefinitely, the universe will eventually become cold, empty, dead. Not for trillions of years, but eventually, the solar system will be long gone by then. The sun will have died. Earth will have been incinerated. Life will have ended. And the universe will continue alone forever. That's not a happy ending in some sense, but it's a real one. It puts our solar system in perspective. We're not permanent. Nothing is. But we exist now, in this moment, in this solar system, in this universe. And that existence is remarkable. So, to return to where we started, something disturbed a cloud 4.6 billion years ago. And that disturbance set off a chain of events: gravity, accretion, migration, impact, bombardment, emergence of life, evolution, consciousness, leading to this moment, to us, asking questions about where we came from. And the answer is, we came from contingency, from chance, from a specific sequence of unlikely events that could have gone differently. We are the products of chaos organized by gravity, of violence that created stability, of hell that birthed life. And we are temporary. Our solar system will end. Our sun will die. Our galaxy will collide with another. The universe will cool. But not yet, not for billions of years. And in the meantime, we're here, conscious, aware, capable of wonder. And that's enough. That's more than enough, because it means the universe, through a long and improbable chain of events, has become aware of itself. The solar system didn't just form, it's formed in such a way that it could eventually understand its own formation. That's not a small thing. That's everything. You're standing on something that shouldn't exist. Not because the ground beneath your feet is unstable, though technically it is, but because the Earth itself is a cosmic accident. A collision so violent, so impossibly perfect in its chaos, that the odds of you standing here right now are almost incomprehensible. And what's wilder, the story of how we got here isn't ancient history anymore. It's science that's still being rewritten in real time. 4.5 billion years ago, there was no Earth. There was no you. There wasn't even a solar system yet. What existed instead was a cloud, not the fluffy white thing you see in the sky on a Tuesday afternoon. I'm talking about a massive rotating disk of gas and dust called a nebula. It stretched across thousands of miles. It was cold. It was dark. And it was about to become everything. But here's the thing that blows my mind. Somewhere in that cloud, gravity was playing the ultimate game of cosmic Jenga. The nebula wasn't uniform. It had dense spots, clumps, and gravity, that invisible force that keeps your phone from floating away, was relentlessly pulling these clumps together. Tighter, denser, hotter. The cloud began to collapse inward, spinning faster and faster like a figure skater pulling in their arms. And at the center of this spinning maelstrom, something incredible happened. The sun was born. Now you might think that's the end of the story. Sun made. Done. Check the box. But the leftover material, all that dust and gas orbiting the newborn sun, that's where our story really begins. And this is where things get absolutely mental. That disk of leftover material is going to do something that seems impossible. It's going to organize itself. Billions of tiny particles are going to collide, stick together, and through this process called accretion, they're going to build planets, but not the way you might imagine, not orderly, not predictable. It's going to be chaotic, violent, catastrophic, and it's going to produce a world that will one day birth consciousness itself, and I'll explain why that matters later in this video. Picture this. You have trillions of dust particles, all orbiting the sun in the same disk. They're moving at different speeds. They're colliding constantly. When two pieces collide at the right angle and speed, they stick together. Gravity helps pull them into tighter clumps. These clumps become pebbles. Pebbles become rocks. Rocks become boulders. Boulders become planetesimals. Chunks of rock and ice, sometimes miles across. And planetesimals become protoplanets, the building blocks of actual planets. This all happened in the first million years or so. 1 million years. That's the blink of an eye on a cosmic timescale. But here's where it gets savage. These protoplanets weren't just floating around peacefully. They were competing. They were gravitationally wrestling for dominance in their orbital neighborhoods. And the stronger ones, the ones that had already accumulated more mass, had an advantage. They were like bullies on a playground, except the playground is space and the stakes are planetary existence. In our solar system, something like 50 to 100 protoplanets formed in the inner region where Earth would eventually exist. but only a few survived. The rest? Destroyed, ejected, swallowed. And the survivors didn't get to celebrate for long because they were about to collide with each other in a way that would make the most catastrophic car crash look like a fender bender. This is where I need to tell you about something that scientists didn't even know was real until about 30 years ago. And when they figured it out, it completely changed how we understand the Earth's origin story. In 1984, scientists noticed something strange in moon rocks brought back by Apollo astronauts. The isotopic composition, basically the fingerprint of the lunar material, was almost identical to Earth's. Not similar, identical. How is that possible? If the moon formed elsewhere in the solar system and Earth captured it, their chemical signatures should be different. But they weren't. This led to a wild hypothesis that seemed insane at first. What if the moon wasn't captured by Earth? What if it was born from Earth? What if our planet collided with another world and the debris from that collision coalesced into the moon? They called it the giant impact hypothesis. And it's probably the most dramatic moment in Earth's entire history. Picture this, because this is real. About 4.51 billion years ago, Earth, which by that point was roughly Mars-sized, maybe 50 to 60% of its current mass, was minding its own business, orbiting the sun. It had cooled enough to have a solid surface. Maybe it had water. Maybe there was the building blocks of chemistry that could lead to life. And then, without warning, another planet-sized object came screaming through the solar system at speeds we can barely comprehend. This object, which scientists call Theia, after the Greek Titan, was roughly the size of Mars. It was moving at about 4 kilometers per second. When it hit Earth, the impact wasn't like anything you've ever experienced. It wasn't even like a nuclear bomb. A nuclear bomb is a firecracker compared to what happened next. The collision was so violent, so energetic, that it instantly vaporized both objects' outer layers. The heat generated was estimated to be around 10,000 Kelvin. That's hotter than the surface of the sun. The force of the impact was so immense that it actually tilted Earth's axis. This tilt is the reason we have seasons. This random collision billions of years ago is why you experience spring, summer, fall, and winter. But wait, there's something even wilder hiding in that impact that I'll come back to in just a moment. The collision ejected an enormous amount of material into orbit around Earth. Some of it fell back to Earth. Some of it escaped to space. But a significant portion, material from the outer layers of both Theia and Earth, coalesced into orbit, and over the course of months to years, that material gravitationally assembled into the moon. The moon didn't descend from heaven. It rose from the ashes of a planetary catastrophe. And here's what's absolutely mind-bending. If Theia hadn't hit Earth, if that collision had never happened, the Earth would be a completely different planet. It might have rotated much faster. It might not have had liquid water on its surface. It might have ended up more like Venus, a hellscape with surface temperatures hot enough to melt lead. The very existence of the moon, which stabilizes Earth's axial tilt, regulates our tides, and gradually slowed our planet's rotation to a speed that allowed life to flourish. All of that came from a cosmic accident. We exist because of a collision that shouldn't have happened. Life on Earth, every tree, every ocean, every conscious being, traces its origin back to the moment another world slammed into ours and nearly destroyed everything. Now, after the giant impact, Earth wasn't done being chaotic. Not even close. The planet that emerged from that collision was a hellscape. It was a molten ball of rock. The entire surface was covered in magma, literally liquid rock reaching temperatures of over 1,200 degrees Celsius. There were no continents. There were no oceans. The atmosphere wasn't made of nitrogen and oxygen like today. It was hydrogen, helium, methane, and ammonia, a toxic brew that would kill you instantly. But something remarkable was happening beneath the chaos. Earth was becoming differentiated. Picture a pot of oil and water that's being stirred violently. The two liquids are mixed together, but if you let it sit, gravity will do its thing. The denser water sinks. The lighter oil rises. It's the same with Earth's interior. In that primordial magma ocean, heavier elements, particularly iron and nickel, were sinking toward the center, while lighter elements were floating toward the surface. This process, called planetary differentiation, created the structure of Earth that we know today. An iron core at the center, surrounded by a rocky mantle, topped with a thin crustal layer. This structure wasn't predetermined. It emerged from the laws of physics and chemistry interacting with planetary scale violence. The core of the Earth, that ball of iron and nickel at our planet's center, is partially molten. It's still hot from that primordial heat, and it's kept warm by radioactive decay of elements like uranium and thorium deep in the interior. This molten iron core does something extraordinary. It generates Earth's magnetic field. Without this magnetic field, life on Earth would be fundamentally different. Solar wind, charged particles streaming from the sun, would slam directly into our atmosphere, stripping it away over millions of years. We'd become a dead planet like Mars. But because of that molten iron core and the dynamo effect it creates, we have a protective magnetic shield surrounding our planet. It's invisible, but it's everywhere. Right now, it's shielding you from radiation. This magnetic field exists because of the way Earth formed, because of the giant impact, because of a chain of events that began with a rotating nebula of dust and gas nearly 5 billion years ago. But the story gets even more interesting when we talk about water. Where did Earth's water come from? This is a question that scientists debated for decades, and the answer is genuinely surprising. For a long time, people assumed that Earth formed from dry materials, and water was delivered later by comets and asteroids. It made intuitive sense. The inner solar system was hot, so water would have evaporated, right? The water must have come from elsewhere. But here's where things get weird. Modern analysis of meteorites and asteroids shows that many of them contain water, frozen water in the form of ice. And some of that water would have survived the impact that created Earth because not all of it would have been vaporized. Some would have been incorporated directly into the young planet. Additionally, and this is where it gets obscure, isotopic analysis of water on Earth suggests that much of it did come from beyond the asteroid belt, from the outer solar system where it was cold enough for water to remain frozen. This water was delivered by what scientists call late Veneer impacts, asteroid bombardments that brought water, organic compounds, and other ingredients for life to the early Earth. But here's the thing that blows my mind. The delivery of this water wasn't random. It was directed by the gravitational architecture of the young solar system. The giant planets, Jupiter, Saturn, and the others, were migrating through the solar system, their orbits changing due to interactions with the disk of material around the sun. This migration scattered asteroids and comets in all directions, including toward the inner solar system where Earth was. In other words, Earth didn't just passively receive water. The structure of the entire solar system, the positions of the giant planets, their orbital dynamics, all of that shaped what materials Earth would receive and therefore what kind of world Earth would become. The young Earth was being bombarded constantly. There was a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, when impacts were particularly intense. Asteroids ranging from tens of kilometers across to thousands of kilometers across were slamming into the surface regularly. Each impact added energy to the planet. Each impact added material. Each impact contributed atoms that would eventually become part of every living thing on this planet. Now, I want to take a step back here because there's something philosophical happening that I think matters. Most of us grow up thinking of Earth as this static thing. We look at it, we think it's always been here, always looked like this, always will be this. But the truth is that Earth is a dynamic, evolving system. It was born, it changed dramatically, and it's still changing today, though on a slower timescale than in its infancy. When I first learned about the giant impact, about the moon being born from a collision, I had this visceral reaction. It was like learning that the ground beneath my feet wasn't just ground, it was a survivor. It was the product of cosmic violence that could have easily ended differently, and that actually matters for how you think about existence. We have this intuition that things are static, that the world is the way it's supposed to be. But every time you study history, whether it's human history or planetary history, you realize that contingency is everything. Small changes in initial conditions lead to wildly different outcomes. If that asteroid had hit Earth at a slightly different angle, it might have destroyed the planet completely instead of creating the moon. If Earth had formed farther from the sun, water would have frozen solid. If it had formed closer, the oceans would have boiled away. But it didn't. The conditions were just right, in a way that seems almost miraculous when you think about it statistically. Let me tell you about something else that happened during Earth's formation that most people don't know about. The late heavy bombardment. So we know about the late heavy bombardment, right? The period of intense asteroid impacts between 4.1 and 3.8 billion years ago. But more recent research has suggested that there might have been an even later period of intense bombardment, possibly extending into the Archean eon. We're talking about impacts that occurred after the conditions for life had already begun to form on Earth. This raises an absolutely wild question. What if some of those later impacts actually helped create the conditions for life? Some scientists have proposed that asteroid impacts, while catastrophic, could have actually created hydrothermal systems, places where hot water from Earth's interior mixed with the ocean. These hydrothermal vents are now known to be potential cradles for life's emergence. They provide chemical energy gradients, they provide minerals, they provide protection. So the very bombardment that seemed like it would sterilize Earth might have actually seeded it with the chemical complexity needed for life to begin. It's like getting struck by lightning and somehow becoming more alive because of it. Except it actually happened. Now let's talk about what happened after the bombardment ended, because this is where the story shifts from violence to chemistry. By around 3.8 billion years ago, Earth had cooled enough for a solid crust to form. We have evidence for this from zircon crystals found in Australia, tiny crystals that contain signatures of early continental rocks. The fact that these crystals exist tells us that by 4.4 billion years ago, liquid water and solid crust had already formed on Earth's surface. Think about that. The Earth formed 4.54 billion years ago. By 4.4 billion years ago, in just 140 million years, the planet had already cooled enough to have oceans and continents. That's fast. These early continents weren't like the ones we have today. They were small, fragmented pieces of crust called cratons. They were scattered across a world that looked absolutely alien to modern eyes. The sky would have been orange or brown, not blue. The atmosphere had no free oxygen. The oceans might have been slightly acidic or alkaline depending on the particular chemicals dissolved in them. But something extraordinary was beginning to happen in those oceans. Here's where I need to tell you about a discovery that fundamentally changed our understanding of life's origin. In the 1970s, scientists discovered hydrothermal vents on the ocean floor. These are literally cracks in Earth's crust where superheated water, often over 400 degrees Celsius, is ejected from beneath the surface. The water is rich in minerals and chemical compounds. And around these vents, despite being in the pitch-black depths where no sunlight reaches, life thrives. Tube worms, crabs, bacteria, an entire ecosystem powered not by sunlight, but by the chemical energy of Earth's interior. When scientists realized this, it sparked a revolution in thinking about how life might have originated. Because the traditional narrative was that life needed sunlight. That's how modern life works, through photosynthesis. But what if life didn't start that way? What if life originated around hydrothermal vents in the early oceans, powered by chemical energy rather than solar energy? Some scientists, like Mike Russell, have proposed that life might have emerged in small rocky chambers within hydrothermal vent structures. These chambers would have been natural laboratories, concentrating chemicals, creating pH gradients, providing mineral catalysts. The chemistry inside these chambers could have spontaneously generated the first self-replicating molecules, RNA or something like it. This wasn't just speculation. In laboratories, scientists have recreated these conditions and observed the spontaneous formation of complex organic molecules. They've seen the building blocks of life assemble themselves when you provide the right chemical environment. In other words, life didn't require some miraculous spark. It required the right chemistry. And those hydrothermal vents provided exactly that chemistry. And where did those hydrothermal vents come from? From Earth's internal heat, which came from the gravitational energy of accretion during Earth's formation and from radioactive decay of elements in Earth's interior. Elements that were created in dying stars billions of years before Earth even existed. Your life traces back through an unbroken chain to the formation of Earth, and before that to the giant impact, and before that to the collapse of a nebula, and before that to the death of stars, and before that to the Big Bang itself. You are made of stardust. That's not poetic metaphor. That's literal chemistry. The iron in your blood was forged in a dying star. The calcium in your bones was created in stellar furnaces. The carbon in your DNA came from thermonuclear synthesis. You are the universe experiencing itself. Let me tell you about something that happened around 2.4 billion years ago that almost ended everything for life on Earth. It's called the Great Oxidation Event, and it's possibly the most catastrophic environmental change in Earth's history. Around 3.5 billion years ago, the first photosynthetic bacteria evolved. They were simple organisms, prokaryotes, but they had a revolutionary ability. They could capture sunlight and convert it to chemical energy through photosynthesis. This is incredible, right? Except for one major problem. Photosynthesis produces oxygen as a waste product. For millions of years, this wasn't a big deal. The oxygen produced by these early bacteria was immediately absorbed by the oceans and rocks. It reacted with dissolved iron in the oceans, forming iron oxide minerals that rained down to the ocean floor. This actually created the massive iron ore deposits that we mine today. Iron ore formations that contain billions of years of accumulated oxygen. But eventually the system couldn't keep up. By 2.4 billion years ago, oxygen began to accumulate in the atmosphere. And for almost all the life that existed at the time, oxygen was a poison. Most organisms on Earth at that time were anaerobic. They didn't need oxygen, and many of them were killed by it. It was an extinction event. Some scientists call it the oxygen catastrophe. Life on Earth nearly ended not because of an asteroid, not because of excessive heat or cold, but because the byproduct of photosynthesis, the very process that would eventually create all the oxygen-dependent life on modern Earth, was toxic to the organisms that existed at the time. But some organisms adapted. They evolved the ability to use oxygen for respiration, which is actually more efficient than anaerobic metabolism. They survived, they thrived, and from these oxygen breathers came all the complex multicellular life we see today. In other words, life on Earth was almost wiped out by its own success. The biosphere nearly destroyed itself, and only because some organisms adapted did life persist and eventually flourish. I want to bring this back to something personal for a moment because I think it matters. When I was in high school, I learned about Earth's formation as a series of facts to memorize. The nebula, the accretion, the differentiation, the giant impact. It all felt disconnected, like a sequence of events that happened and then stopped being relevant. But as I got older, I realized something. These events aren't historical footnotes. They're the foundation of everything about our world and our existence. The reason we have seasons is because of the giant impact. The reason we have a magnetic field that protects us from radiation is because of Earth's molten iron core, which exists because of the way planetary differentiation worked during Earth's formation. The reason we have water on the surface is because of late Veneer impacts. The reason we have the chemical diversity necessary for complex chemistry is because of how our solar system formed. And more profoundly, the reason any of us exist at all is because of an incomprehensible chain of contingencies. If the nebula had collapsed slightly differently, if Theia had hit at a different angle, if the late bombardment hadn't delivered the right mix of materials, if oxygen hadn't accumulated in the atmosphere at exactly the right time, we exist in a razor-thin margin between a universe that would be inhospitable to life and one that is. And that margin came about through billions of years of planetary violence and evolution. That should make you feel something. That should change how you think about your place in the cosmos. Now, there's one more piece of this story that I think is worth exploring because it takes us from Earth's formation into Earth's present. The planet we live on today is not the same as the planet that formed 4.54 billion years ago. Continents have moved. The magnetic field has fluctuated and even reversed polarity. The composition of the atmosphere has changed radically. The climate has shifted between ice ages and warm periods. And all of that is still happening. In the last 200 years, humans have altered the composition of the atmosphere more than nature altered it in the previous 200,000 years. We've increased carbon dioxide by 50% since the Industrial Revolution. We're causing the 6th mass extinction in Earth's history. We're changing the climate at a rate that's unprecedented in the Holocene, the current geological epoch. But here's the thing that I think matters. The Earth that formed from cosmic violence, that survived asteroid bombardments, that overcame oxygen catastrophes and ice ages and volcanic eruptions, that Earth has enormous resilience. Life on Earth has faced extinction events and adapted. The biosphere has evolved new strategies and new forms, but resilience isn't infinite, and adaptation requires time. We're changing the conditions on Earth faster than biological systems can adapt. That's the core of the problem, not that the planet is fragile. It's not. but that we're pushing it faster than it can respond. And I think understanding how Earth formed, how precarious the conditions for life actually are, how contingent our existence is on a very specific set of circumstances, I think that understanding changes how you should think about stewarding this planet. We live on a survivor, a world that emerged from cosmic violence and evolved into an oasis of life in an otherwise sterile universe. The least we could do is not break it. So here's what we've covered. Earth formed 4.54 billion years ago from the collapse of a nebula. It accreted material through billions of collisions over millions of years. It was impacted by a Mars-sized object called Theia, which created the moon and tilted Earth's axis. The planet differentiated into a core, mantle, and crust. It was bombarded by asteroids that delivered water and organic compounds. Hydrothermal vents created the chemical conditions for life. Photosynthetic bacteria evolved and filled the atmosphere with oxygen, nearly killing everything before life adapted. Continents formed, oceans formed, and eventually the conditions became right for the emergence of consciousness. All of that, billions of years of planetary evolution, led to this moment. You reading this, me writing this. The existence of every conscious being on Earth. And it all traces back to a rotating cloud of gas and dust, and to the laws of physics that caused it to collapse. The Earth wasn't made for us. We were made by Earth. We're not separate from this planet. We're an emergent property of it. We're the universe becoming conscious of itself, an outgrowth of the same forces that assembled atoms into rocks, and rocks into planets, and planets into worlds. That's not just science. That's something approaching wonder. That's something that should change how you see yourself and your place in this cosmos. Right now, at this exact moment, the sun is burning 600 million tons of hydrogen every single second. Not slowly, not gradually. Every second, 600 million tons. And it's been doing this for 4.6 billion years. And it's going to keep doing it for another 5 billion years before it dies. That's an incomprehensible amount of energy. And here's the wild part. That energy is the only reason you exist. Every photon that hits your skin, every calorie you eat, every breath you take, all of it traces back to nuclear fusion happening 93 million miles away in a massive ball of plasma that we mostly ignore because we've gotten used to it being there. But the sun wasn't always burning. It wasn't always there. And the story of how it formed is a story about gravity, about pressure, about the moment when a cloud of dust and gas collapsed under its own weight and ignited into the most powerful nuclear reactor in our solar system. This is the story of the most important event in your existence. Let me take you back 4.6 billion years ago to a place that looked nothing like our solar system today. There was no sun. There were no planets. There wasn't even a defined solar system yet. What existed instead was a giant cloud of gas and dust, a nebula stretched out across light years of space. This wasn't concentrated. It wasn't dense. It was mostly empty space. If you could somehow travel through this cloud, you'd pass through regions of incredible emptiness, punctuated by thin wisps of material. This nebula was cold. We're talking maybe 10 Kelvin, just barely above absolute zero. And it was dark. There was internal light source. The only thing illuminating it would have been distant starlight from other stars in the galaxy. But this nebula had something crucial. It had angular momentum. It was rotating. Think of it like a figure skater spinning slowly with their arms outstretched. Now imagine the figure skater is spread out across light years, and is made of gas and dust. That's your nebula. And like the figure skater, it was spinning. Now here's where gravity enters the story and things get intense. Within this nebula, the material wasn't uniformly distributed. There were regions that were slightly denser than others. Maybe a dust grain collided with another dust grain. Maybe a few hydrogen molecules clustered together. These tiny variations in density shouldn't matter in a cloud as vast as this. The gravitational pull should be negligible. But gravity is relentless. It's patient. It's the most powerful force in shaping the universe on large scales, and it was about to prove it. In one particular region of this nebula, a region that happened to be part of a larger molecular cloud called the solar nebula, gravity began to amplify those tiny density variations. More mass accumulated in the slightly denser regions. This increased their gravitational pull, which attracted more material, which increased the gravitational pull even more. It was a feedback loop, a runaway process. And somewhere around 4.6 billion years ago, something triggered the collapse of this particular region. It might have been a nearby supernova. The shockwave from a dying star could have compressed the cloud. It might have been the collision with another cloud of interstellar gas. Whatever the trigger was, the collapse began. And once it began, there was no stopping it. The cloud started to collapse inward. Gravity was pulling everything toward the center. And remember that angular momentum, that spin. As the cloud collapsed, it spun faster. This is the same reason an ice skater spins faster when they pull their arms in. The angular momentum has to go somewhere. So the collapsing cloud didn't collapse into a sphere. It collapsed into a disk. Picture a spinning frisbee. That's roughly what you have. A rotating disk of gas and dust with most of the material concentrated toward the center and material spread out in a flattened plane around it. This is the solar nebula. This is where our sun was about to be born. Now, the center of this disk was where things got absolutely insane. As the cloud collapsed, gravitational potential energy was converted into heat. I need to explain what that means because it's crucial to understanding how the sun formed. Imagine you drop a ball from a tall building. As it falls, gravity does work on it. That gravitational potential energy gets converted into kinetic energy, the energy of motion. The ball speeds up, but if the ball hits the ground and stops, that kinetic energy has to go somewhere. It turns into heat and sound. The impact creates vibrations in the ground and in the air. Now, imagine doing this with trillions of particles in a collapsing cloud. Each particle is falling inward under gravity. Each particle is accelerating. And when particles collide, which happens constantly in a dense region, all that kinetic energy converts into heat. At the center of the collapsing nebula, in a region maybe a few times the size of our solar system, particles were falling inward and colliding at incredible speeds. The heat generated was astronomical. Literally, the temperature began to rise rapidly. After about 100,000 years of collapse, the core temperature reached around 10,000 Kelvin. After 200,000 years, it was 100,000 Kelvin. After 500,000 years, it had reached about 1 million Kelvin. And it kept climbing. At these temperatures, the normal rules of chemistry break down. Molecules can't exist. Atoms themselves are torn apart into plasma, a soup of electrons and nuclei separated from each other, responding to electromagnetic forces. The core was becoming a stellar furnace. But there's a threshold, a critical temperature where something fundamental changes. When the core temperature reaches about 10 million Kelvin, something extraordinary happens. Hydrogen nuclei, which are just protons at this point, start to have enough energy to overcome the electrostatic repulsion between them. They can get close enough for the strong nuclear force to take over. And when that happens, they can fuse, they can merge together and form heavier elements. And that process, nuclear fusion, releases enormous amounts of energy. This is the moment the sun was born. It's not that the sun suddenly appeared in a flash of light. That's not how it worked. Instead, the core gradually accumulated more mass, got hotter and hotter, reached critical temperature, and then fusion began. And once fusion began, something remarkable happened. The core temperature stabilized. Here's why. Before fusion starts, the core is heating up because gravity is compressing the material. But once fusion begins, it produces energy. That energy creates pressure that pushes outward against gravity's inward pull. The core reaches an equilibrium, gravity pulling in, radiation pressure pushing out. And this equilibrium maintains a stable temperature where fusion can continue indefinitely. This is a state called hydrostatic equilibrium, and it's what makes the sun, well, the sun. The young sun at this point wasn't the same as it is today. It was slightly cooler, it was smaller, but it was already a working fusion reactor. And this is an obscure fact that most people don't know. The very young sun, sometimes called the T Tauri sun or the T Tauri stage, was actually less luminous than it is today. This is called the faint young sun paradox, and it creates a genuine puzzle about how life emerged on early Earth, given that the sun was dimmer. But that's a story for another time. The point is, the sun had formed, and its formation had consequences that rippled outward throughout the entire solar system. Let me tell you about what happened around the sun in the disk, because this is where the story connects to everything that came after. When the sun formed and fusion began, it created a stellar wind, a stream of charged particles flowing outward from the sun's surface. This wasn't gentle, it was intense. Particles were being ejected at speeds of hundreds of kilometers per second. This stellar wind had an effect on the surrounding disk. It began to blow away the light gases, hydrogen and helium, from the inner regions of the solar nebula. The disk that had been made of roughly 98% hydrogen and helium suddenly lost those elements in the inner regions, leaving behind only the heavier elements, metals and rocks. This created a gradient in the solar system. The inner regions became rocky. The outer regions retained their hydrogen and helium. And this division is why the inner solar system has rocky planets like Earth and Mars, while the outer solar system has gas giants like Jupiter and Saturn. But that's just one effect. The young sun also created heat. In the inner solar system near the sun, temperatures were extremely high. In the region where Earth would eventually form, temperatures were probably above the melting point of metals. The dust and gas that would become planets was being baked. Water couldn't condense. Ice couldn't form. It was a scorching, dry environment. But in the outer solar system, beyond a certain distance called the frost line or snow line, temperatures were cool enough for water ice to condense. This is where icy bodies could form. This is where the building blocks of gas giants were created. In other words, the sun's formation shaped the entire structure of the solar system. The placement of the sun, its mass, its luminosity, all of that determined what kinds of planets could form where. Now, there's something profound I want to explore here because it connects to the bigger question of why we're here. The sun's formation wasn't inevitable. The collapse of the solar nebula could have happened differently. The mass that accumulated at the center could have been slightly more or slightly less. If it had been slightly less, maybe 70% of the sun's actual mass instead of 100%, it wouldn't have gotten hot enough for fusion to begin. It would have become a brown dwarf, a failed star, a dark, cold object floating in space. If it had been significantly more, maybe 20 to 30% more massive, fusion would have begun much more rapidly, and the sun would have burned through its hydrogen fuel much faster. A more massive sun has a much shorter lifetime. Instead of 10 billion years, 5 billion remaining, it might only live a few 100 million years. Not enough time for complex life to evolve on planets orbiting it. In other words, the sun's mass had to be in a very specific range for the conditions necessary for life to emerge. And there's something even wilder. If the solar nebula had been oriented differently, if it had been rotating at a different speed, if gravity had amplified the density variations at a different rate, all of these tiny variations would have produced a different sun, a different solar system, a different set of planets, and ultimately a different history. We exist because the sun's formation happened in a very specific way within a narrow range of possibilities. The fact that we're here is not just unlikely. It's statistically improbable on scales that are hard to wrap your head around. And yet, here we are. Let me tell you about the first few million years after the sun's formation, because this is when things got really intense. The young sun was incredibly active. It had massive solar flares, explosions of magnetic energy on its surface that could release as much energy in seconds as the sun normally releases in a day. These flares ejected cosmic rays and charged particles into the surrounding solar system. They created a hostile environment. The disk of material around the young sun was chaotic. Dust particles were colliding, merging, and being ejected. The accretion process was violent. It was creating protoplanetary embryos, objects ranging from dozens to thousands of kilometers across. And these embryos were crashing into each other, merging and creating larger objects. This period of intense activity is called the T Tauri phase, named after a class of young stars that show this behavior, and it lasted for roughly the first million years of the sun's existence. During this phase, the young sun was actually more luminous than it is today. Counterintuitive, right? But the intense magnetic activity and the accretion of material onto the sun's surface generated extra energy. The star was hotter and brighter, and then, as the disk cleared out and the magnetic activity settled down, the sun dimmed slightly and settled into the stable, long-lived phase that it's currently in. This settling down process is crucial. If the sun had remained in its chaotic, high-activity state, planets probably wouldn't have formed. The radiation and stellar wind would have blown away the disk before planetary accretion could complete. But the sun's activity quieted down just enough, just at the right time, for planets to assemble. Again, contingency. Again, the razor-thin margin between a universe where we could exist and one where we couldn't. Now I want to tell you something about the sun that most people don't realize. It's a second-generation star. The sun didn't form from primordial material left over from the Big Bang. The atoms that make up the sun, the hydrogen, the helium, and crucially the heavier elements, were created by previous generations of stars. Here's how it works. The very first stars in the universe formed maybe 100 million years after the Big Bang. These were massive stars made entirely of hydrogen and helium, the only elements that existed at that time. These first stars lived fast and died young. Their lifespans were measured in millions of years, not billions. When they died, they exploded as supernovae, and in those explosions, the intense heat and pressure created heavier elements: carbon, nitrogen, oxygen, silicon, iron, all the building blocks of chemistry as we know it. These elements were scattered into space, seeding new nebulae with chemical complexity. Second-generation stars formed from these enriched nebulae. They had heavier elements mixed in with the primordial hydrogen and helium. Some of these second-generation stars also died as supernovae, creating even more heavy elements. The Sun is actually a third or fourth generation star. It formed from a nebula that had been enriched by multiple generations of stellar explosions. The iron in the Sun came from dying stars. The oxygen came from dying stars. The carbon came from dying stars. And here's the profound part. The atoms in your body came from dying stars. The calcium in your bones. The iron in your blood. The carbon in your DNA. All of it was forged in stellar furnaces billions of years ago and scattered into space when those stars exploded. You are literally made of stardust, not metaphorically. Literally, chemically, the atoms that compose you were created in the cores of dying stars. And the Sun, your Sun, the reason you exist, is made of the same material. It's made of the ashes of previous universes' worth of stellar violence. Let me talk about something that doesn't get enough attention: the Sun's chemical composition and what it tells us about the Sun's origin. If you analyze the Sun's spectrum, the light it emits broken down by wavelength, you can determine what elements are present. And what scientists found is that the Sun has a specific ratio of heavy elements to hydrogen and helium. This ratio is called metallicity in astronomy. And yes, astronomers call everything heavier than helium a metal, which confuses everyone. The Sun's metallicity is higher than stars that formed earlier in the galaxy's history, but lower than stars that formed more recently. This places the Sun in a specific generation of stars. It tells us when the Sun formed relative to other stars in the galaxy. And here's something wild. The Sun's metallicity is nearly identical to the metallicity of other stars in a group called the galactic disk population. These are stars that formed around the same time as the Sun, in roughly the same region of the galaxy. Some of these stars are still nearby, within a few hundred light years, and some have drifted far away. But here's the truly obscure fact that blows my mind. Astronomers have identified a group of stars with the same metallicity and age as the Sun, and they believe these stars formed in the same star cluster as the Sun. They were born together. They are, in a sense, the Sun's siblings. Over time, these stars drifted apart due to gravitational interactions in the galaxy. They're now scattered across light years of space, but they share a common origin. They formed together in the same nebula, from the same cloud of material, 4.6 billion years ago. The Sun wasn't born alone. It was born in a stellar nursery with thousands of other stars, and it has siblings scattered throughout. I want to talk about something that's genuinely profound: the Sun's lifetime and what it means for consciousness. The Sun, in its current state, fusing hydrogen in its core, will persist for roughly 10 billion years total. It's currently about 4.6 billion years old, so it has about 5.4 billion years remaining. This is called the main sequence lifetime, and it's the stable phase where the Sun will remain roughly constant. But here's what matters. The timeline for life's emergence on Earth is incredibly tight. Life emerged on Earth roughly 3.7 to 3.8 billion years ago, just about a billion years after the planet formed. Complex multicellular life didn't emerge until about 600 million years ago. Mammals didn't appear until 200 million years ago. Primates didn't appear until 60 million years ago. Humans didn't appear until 300,000 years ago. In other words, consciousness, at least as we understand it, emerged in the last 300,000 years of the sun's 10 billion year lifespan. That's the last 3% of the sun's life, the last hair's breadth of cosmic time. If the sun had been slightly more massive, it would have burned through its fuel much faster. Consciousness wouldn't have had time to emerge. If the sun had been slightly less massive, it would have been dimmer, and the early Earth might have been too cold for life. Either way, we wouldn't be here. The sun's formation had to happen at exactly the right time in the galaxy's history, producing a star of exactly the right mass, in a location with exactly the right chemical composition for consciousness to eventually emerge. The probability of this happening is so vanishingly small that if you tried to express it as a decimal, you'd run out of zeros before you finished writing it down. And yet, here you are, reading this, conscious, aware, able to comprehend the story of your own origin. Now let me tell you something about the sun that's genuinely unsettling. It's dying. Not imminently. Not in your lifetime or anyone else's for billions of years. But the sun is in a long, slow process of death. And when it dies, it will transform everything in the solar system. In about 5 billion years, the sun will begin to run out of hydrogen in its core. Fusion will slow down. The core temperature will drop slightly. And here's where something remarkable happens. The sun will contract. Gravity will pull the core inward more forcefully. As the core contracts, it heats up. And as it heats up, the layers above the core heat up too. Eventually, hydrogen fusion will begin in a shell surrounding the core, the hydrogen that wasn't hot enough to fuse when the core was cooler. This shell burning produces more energy than core burning did. The sun will expand dramatically. It will become a red giant, swelling to something like 200 times its current size. If the sun were scaled to this size, it would engulf Mercury, Venus, and possibly Earth. The surface temperature will actually cool down as the sun expands. Counterintuitive, right? But that's how stellar physics works. The energy is being spread over a much larger surface area. The sun will become a red giant, glowing dimly from its vastly expanded surface. And then, after a few billion years in this phase, the sun will shed its outer layers. The core will be exposed. All that material will drift away into space, and what remains will be a white dwarf, a tiny Earth-sized remnant of the sun, incredibly dense, slowly cooling over the course of trillions of years. This is the fate of the sun. This is what the end of our star looks like. And it's both beautiful and terrifying. But I don't want to end on that note because there's something more important to explore. The sun's formation, its stability, its lifespan, its fate, all of this is intimately connected to consciousness and meaning. And I think that connection is worth sitting with. For most of human history, we didn't understand the sun. We worshipped it. We created myths about it. The Egyptians imagined a god named Ra sailing a boat across the sky. The Greeks imagined Apollo driving a chariot pulled by horses. The Aztecs believed the sun needed human sacrifices to keep rising. These weren't absurd beliefs. They were reasonable attempts to make sense of the most important object in the sky. The object that literally kept us alive. The object whose disappearance for a few hours each day caused fear. The object that determined seasons and harvests and survival, but we didn't understand, what the sun actually was. And then in the 20th century, we figured it out. We realized that the sun is a nuclear reactor, that it's powered by fusion, that it converts 600 million tons of hydrogen into helium every second, that it's been doing this for 4.6 billion years, that it will continue for another 5 billion years. And in understanding what the sun actually is, we gained something profound: perspective. We realized that the sun is not eternal. It's not a god. It's a star. It's a temporary phenomenon on cosmic timescales. And that means everything the sun illuminates, including us, including consciousness itself, is also temporary. And yet that impermanence is what gives life meaning. If the sun were eternal, if the solar system were stable forever, if consciousness had infinite time ahead of it, then there would be no urgency, no reason to value this moment, no reason to appreciate the fact that you're alive right now, right at this moment when conditions are perfect for consciousness. But the sun is dying. Slowly, gradually, over billions of years, but inevitably it's moving toward its end. And that creates an urgency, a meaning. I want to share something personal here because I think it matters in the context of understanding the sun. The first time I really internalized that the sun was dying, I had a strange reaction. I wasn't afraid. I wasn't sad. I was awed. I was struck by the realization that I lived during one of the few billion-year windows in the sun's 10 billion year history when conditions were right for consciousness. I lived at a time when the sun was stable, when Earth had liquid water, when complex life had emerged, when consciousness had emerged. I existed in the narrow, sweet spot of cosmic time when all these things aligned. And that made me value this moment differently. It made me realize that the unconscious universe, the vast majority of cosmic time and space, is just that: unconscious, unaware. The sun shines on empty worlds for billions of years. But here, on this planet, orbiting this star, for this brief window of cosmic time, consciousness emerged. We are the universe becoming aware of itself. We are stardust organized in such a way that it can contemplate its own origin. We are the product of 13.8 billion years of cosmic evolution, from the Big Bang to this moment. And the sun is the reason we exist. Let me tell you something else about the sun that connects to a bigger question. Why does fusion work at all? Fusion requires overcoming the electrostatic repulsion between positively charged nuclei. This shouldn't work in many cases. The repulsion is so strong that the nuclei should bounce apart before they get close enough for the strong nuclear force to take over. And yet, fusion happens in the sun constantly. Why? Because of quantum tunneling. Quantum tunneling is a phenomenon where particles can appear on the other side of an energy barrier, even though they don't have enough energy to classically overcome that barrier. It's like throwing a ball at a wall and occasionally finding that the ball has passed through the wall and appeared on the other side. This sounds impossible. It violates our everyday intuition about how physics works. But at quantum scales, it's real. It's been experimentally verified countless times, and it's essential for the sun to work. Without quantum tunneling, the sun wouldn't fuse hydrogen. Without the sun fusing hydrogen, there would be no light, no heat, no life on Earth. Without quantum tunneling, a phenomenon that seems to violate classical physics but is fundamental to quantum mechanics, you wouldn't exist. This is one of those facts that blows my mind. Your existence depends on a quantum mechanical phenomenon that doesn't make intuitive sense. Your existence depends on a universe operating according to rules that are stranger than fiction. Now let me bring this back to something practical, because understanding the sun isn't just about cosmology and philosophy. It has real implications for life on Earth right now. The sun's energy output is slowly increasing. This is called the faint young sun paradox I mentioned earlier, but from the opposite direction. As the sun ages, it actually gets slightly brighter. Its luminosity increases by roughly 10% every billion years. This has profound implications. In 1.1 billion years from now, the sun will be bright enough that the greenhouse effect will cause runaway water vapor evaporation on Earth. The oceans will boil away. Earth will become a dead, lifeless planet. That's not a metaphor. That's not speculation. That's a direct consequence of stellar evolution. In 1.1 billion years, Earth will no longer be habitable. Life on Earth, in its current form, has maybe a billion years left. After that, the sun's increasing luminosity will have made our planet uninhabitable. Complex life might persist longer through adaptation, but eventually the sun will have boiled away Earth's water completely. And after that, in another 4 billion years, the sun will enter its red giant phase and expand to engulf Earth entirely. This timeline might seem distant. It might seem irrelevant to your life right now. But it's real. It's inevitable. Barring some future technology we can't currently imagine, this is the fate that awaits Earth. And that changes how you should think about the present moment. We live during a window of habitability, a window that's closing gradually but inevitably. We have a billion years, which sounds like forever until you remember that the sun has already existed for 4.6 billion years. We're at the midpoint of habitability. We're at the peak. And from here on out, it's a slow decline. That should change your perspective on this planet, on this moment, on the urgency of protecting life while we still can. Let me talk about something that's been bothering scientists for decades. The solar neutrino problem. The sun produces neutrinos as a byproduct of fusion. These are ghostly particles that barely interact with matter. Trillions of them pass through your body every second, and you'll never notice them. They pass through the entire Earth as if it weren't there. In the 1960s, scientists built detectors to measure the number of neutrinos coming from the sun, and they found something puzzling. There were fewer neutrinos than theoretical models predicted, about a third fewer. For decades, this was a genuine mystery. Either the sun wasn't fusion-powered, which didn't make sense given everything else we knew about it, or our models were wrong, or something weird was happening to the neutrinos on their way to Earth. Then, in the 1990s, scientists discovered that neutrinos have mass, something they thought was impossible. And they discovered that neutrinos can change flavor, oscillate between different types. This explained the discrepancy. The neutrinos were being produced at the predicted rate, but they were transforming into types of neutrinos that the detectors couldn't easily measure. This discovery was huge. It revealed something fundamental about particle physics, and it came about because scientists were trying to understand the sun. This is a perfect example of how studying astrophysics leads to discoveries in fundamental physics. The sun isn't just important because it keeps us alive. It's a laboratory for understanding the deepest laws of nature. Here's another thing about the sun that's genuinely wild. It has a core, but the core isn't where all the fusion happens. In the sun's core, temperatures are around 15 million Kelvin. Fusion happens here, but it's not efficient. Most of the hydrogen in the core is too cool to fuse. Even though 15 million Kelvin sounds impossibly hot, it's actually on the cool side for the sun's core given the pressures involved. But the sun's core is only about 25% of the sun's radius. The rest of the sun, the radiative zone, and the convective zone above the core contains most of the sun's mass and material. And yet, almost all of the sun's energy comes from that tiny core. It's like having a massive factory where 99% of the building is just storage and processing, and 1% of the building does all the actual work. The sun is incredibly inefficient at converting its mass into energy. Only about 0.7% of the hydrogen that the sun will ever burn will actually undergo fusion. The rest will be left behind when the sun dies. But that 0.7% is enough to power the sun for 10 billion years. That's how powerful fusion is. That's how much energy is released when you convert mass into energy, according to E equals mc squared. Now, I want to talk about something that might seem off topic, but I promise it connects. The sun's role in shaping human consciousness and culture. Every human culture has myths and stories about the sun. The Egyptians had Ra. The Greeks had Apollo. The Inca had Inti. The Japanese have Amaterasu. The Aboriginal Australians have stories of the sun woman traveling across the sky. This isn't coincidence. The sun is the most important object in our sky. It determines day and night. It determines seasons. It determines whether crops grow. It determines survival. So every human culture developed stories to make sense of it. Stories to explain why it rises and sets. Stories to give it meaning. Stories that embedded our dependence on the sun into our collective consciousness. And these stories, while not scientifically accurate, captured something true. The sun is a source of life. The sun is powerful. The sun deserves reverence. In a sense, ancient humans understood something that we, modern, scientifically educated people sometimes forget. The sun is not just a giant ball of gas undergoing nuclear fusion. It's the source of everything we care about. It's the reason we exist. Science has taught us what the sun actually is. But it shouldn't teach us to stop caring about it. If anything, understanding the sun's physics, understanding that it's a finite resource that will eventually die, should deepen our appreciation for it. Let me tell you about something called the solar dynamo because it's genuinely fascinating and most people have no idea it exists. The sun has a magnetic field. You probably know that. The magnetic field is responsible for sunspots, solar flares, and solar prominences. But here's what's wild. The sun's magnetic field is generated by the motion of plasma in the sun's interior. Deep in the sun, in the radiative zone, hot plasma moves in complicated patterns. These moving charged particles generate magnetic fields. The fields interact with the plasma, which changes how it moves, which changes the magnetic fields. It's a complex feedback system, and the result is that the sun's magnetic field is constantly changing. It's not static, it's dynamic. It oscillates with a period of about 11 years. Every 11 years, the sun's magnetic field flips polarity. North and south swap places. This 11-year cycle has huge effects on Earth. During solar maximum, when the magnetic field is most active, there are more sunspots, more solar flares, more solar wind. During solar minimum, the opposite is true. And this variation affects Earth's upper atmosphere, which affects our climate, which affects weather patterns, agriculture, and human civilization. So indirectly, through the solar dynamo and the 11-year solar cycle, the sun is influencing human history. Wars have been fought, civilizations have risen and fallen, and some of that might be connected to solar activity affecting climate and crops. We don't usually think about the sun as a factor in human history, but it is. The sun is always there, shaping the conditions of our existence. I want to explore something more philosophical now, the relationship between consciousness and the sun. The sun created the conditions for life to emerge on Earth. But did the sun create consciousness? That's a deeper question. Consciousness emerged through evolution. Billions of years of life formed struggling to survive, reproducing, passing on their genes, accumulating small changes that led to larger changes. Eventually, brains emerged, nervous systems emerged, and at some point, something called consciousness emerged. But all of this was only possible because the sun was shining. Energy flowing from the sun powered photosynthesis. Photosynthesis created the oxygen-rich atmosphere. Oxygen powered more complex organisms. More complex organisms led to more complex brains. More complex brains led to consciousness. So in a very real sense, the sun is responsible for consciousness. Not directly, the sun didn't design brains or write genetic code, but through the long chain of causality stretching back billions of years, the sun is the ultimate source of the energy that allowed consciousness to emerge. You are conscious because the sun exists. Your thoughts are powered by the energy the sun is currently radiating into space. Right now, as you read this, photons from the sun are hitting plants, which are converting that energy into chemical energy through photosynthesis. You eat those plants, or eat animals that eat those plants, and that chemical energy powers your brain. Your brain produces consciousness. The sun doesn't just keep you alive. The sun literally powers every thought you have, every realization, every moment of wonder, every act of love, every discovery. All of it is ultimately powered by fusion reactions in the sun's core. Let me tell you something about the sun that connects to the future, the search for exoplanets. Since 1992, we've discovered over 5,000 planets orbiting other stars. We found planets orbiting in the habitable zones of their stars, regions where liquid water could potentially exist on a planet's surface. We found Earth-sized planets. We found planets that might actually support life. And all of this discovery has been possible because we understand our own sun. By studying how the sun works, by understanding stellar physics, we've developed the tools and knowledge to detect planets around other stars. We've learned what conditions are necessary for life, and we're looking for those conditions elsewhere in the galaxy. But here's the wild part. We've also learned something about the sun's uniqueness. The sun is a G-type main sequence star, a yellow dwarf. There are roughly 7.5% of all stars in the galaxy that are G-type like the sun, but most stars are actually red dwarfs, smaller, cooler, less massive. These are much more common, but red dwarfs are also less stable. They're more prone to flares. Their habitable zones are closer to the star, which means planets are more likely to be tidally locked, always showing the same face to the star. The conditions for life around red dwarfs are less favorable than around G-type stars like the sun. In other words, the sun is actually a relatively good star for hosting life-bearing planets. We're luckier than most planetary systems. We orbit a stable middle-aged star that provides consistent energy for billions of years. This is another example of the exquisite contingency of our existence. We don't just live on a unique planet. We orbit a unique type of star in a unique location in the galaxy. The odds compound. The improbability deepens. Now I want to talk about something that feels relevant to the present moment. The sun as a source of future energy. Right now, humanity uses fossil fuels, ancient sunlight basically. We burn coal and oil that were created from plant and animal matter that lived millions of years ago, powered by the sun of millions of years ago. We're using the sun's old energy, but the sun is still here. It's still radiating energy constantly, and that energy is vastly more than humanity currently uses. The total amount of energy the sun radiates in 1 hour is more than humanity uses in an entire year. 1 hour of sunlight is more energy than we need for a year. And this energy is free. It's renewable. It's available for the next 5 billion years. Solar technology is improving. Solar panels are becoming more efficient. Solar thermal systems are being deployed. And as we shift toward renewable energy, we're essentially shifting toward harvesting the sun's current energy instead of burning its ancient energy. In a sense, this is a return to living in sync with natural energy flows. Indigenous peoples lived on solar energy. They ate food powered by photosynthesis. They used fire powered by ancient sunlight. They navigated by the stars that are also suns. Modern civilization abandoned that model and started burning fossil fuels at an accelerating rate. But the future might involve returning to the sun as our primary energy source, except now we'll do it with technology that lets us harvest that energy efficiently. This is a profound shift, and it's only possible because we understand what the sun actually is. Let me tell you about something called the Hertzsprung-Russell diagram, because it's one of the most important tools in astronomy, and it's based on studying the sun. In the early 1900s, two astronomers named Einar Hertzsprung and Henry Norris Russell independently plotted stars on a graph with luminosity on one axis and temperature on the other. They expected stars to be randomly distributed across the graph. Instead, they found a pattern. Most stars fell along a diagonal line running from cool, dim stars in the lower left to hot, bright stars in the upper right. This line was called the main sequence. And the sun sits right in the middle of the main sequence. Not too bright, not too dim, not too hot, not too cool. This discovery revealed something fundamental. Stars follow a pattern. They're not random. They have structure. And by studying where stars fall on the Hertzsprung-Russell diagram, we can estimate their age, their mass, and their future fate. The sun, being a middle-aged main sequence star, tells us we're at a point in cosmic history where stars like the sun are common. We're not at the beginning of the universe's history, then the only stars would be massive, short-lived stars. We're not at the end, then the only stars would be dead remnants. We're in the middle, when mid-mass stars like the sun are the dominant type. And in this middle era, consciousness has emerged. Consciousness emerges when the universe is old enough for planets to form, but not so old that massive stars have already died and seeded space with heavy elements. Consciousness emerges roughly in the middle of the cosmic timeline. This might not be coincidence. This might be the only time in the universe when conditions are right for consciousness. The first few billion years, not enough heavy elements. The last few trillion years, all the stars are dead or dying. But in the middle, the era of main sequence stars like our sun, consciousness can emerge. I want to end with something that ties everything together, the sun as a window into the universe's nature. By studying the sun, we've learned about fusion. We've learned about nuclear physics. We've learned about stellar evolution. We've learned about the life cycles of stars. We've learned about the origin of elements. We've learned about magnetism and plasma physics and quantum mechanics. The sun is like a cosmic textbook. It teaches us about the fundamental laws of nature. And through understanding the sun, we understand ourselves because we're made of the same material, powered by the same physics, existing within the same universe. The sun is also a mirror. It reflects back to us the fact that we are not special. We're not the center of the universe. We're not eternal. We're temporary. We're small. But paradoxically, this also reveals that we are special in a different way. We are conscious. We are aware. We can contemplate the sun. We can understand it. We can appreciate it. No other known object in the universe has achieved this. No star understands itself. No planet contemplates its position in space. Only here, on Earth, orbiting the sun, has the universe produced something that can think about itself. And that is remarkable. That is worthy of wonder. That is something that should change how you see yourself and your place in existence. The sun wasn't always there. Before 4.6 billion years ago, the sun didn't exist. There was just a nebula, a cloud of gas and dust. And then gravity did its work. Density variations amplified. The cloud collapsed. Heat accumulated. Temperature rose. And then, at a critical moment, fusion began. A new star was born. Our star. The star that would make life possible. The star that would power the emergence of consciousness. For 4.6 billion years, the sun has been burning, every second converting 600 million tons of hydrogen into helium, every second releasing the energy that keeps Earth warm, that powers photosynthesis, that ultimately powers every thought you've ever had. In about 5 billion years, the sun will begin to die. It will expand. It will cool. It will shed its outer layers. And eventually, it will become a white dwarf, a dead remnant, slowly cooling over trillions of years. But between now and then, there is still time. There is still the stable, bright, life-giving sun. There is still the opportunity for consciousness to flourish, to create, to understand, to love. Make use of that time. Appreciate the sun. Understand what it is, not as a mythological object, but as a real physical thing. A massive fusion reactor powered by the crushing pressure of its own gravity, sustained in a delicate equilibrium between inward-pulling gravity and outward-pushing radiation pressure. Appreciate that this equilibrium will not last forever. Appreciate that your consciousness exists only because the sun formed, only because fusion works, only because of billions of years of cosmic evolution that led to this specific moment. The sun created you. The sun powers you. The sun is the reason you exist. And that is something worth understanding, something worth appreciating, something worth wondering about. Right now, between Mars and Jupiter, there's a region of space called the asteroid belt. And in that region, there are millions of objects, rocky, metallic remnants left over from the formation of the solar system. The largest of these objects, Ceres, is so massive that it's classified as a dwarf planet, but the vast majority are smaller, much smaller. Most people think of the asteroid belt as a dense field of rocks, like a cosmic minefield that spaceships have to navigate carefully, dodging left and right to avoid collisions. This image comes from science fiction. It's completely wrong. The asteroid belt is actually mostly empty space. The asteroids are so spread out that if you were traveling through the belt, you'd likely never see another asteroid. They're separated by millions of kilometers. You could cruise through the entire asteroid belt without encountering a single object. And yet these asteroids, these remnants of planetary formation, tell us something profound about how our solar system came to be. They tell us a story of creation and destruction. They tell us about the chaos of the early solar system, and they tell us about our own fragility because some of these asteroids are on collision courses with Earth. This is the story of the asteroids, what they are, where they came from, and why they matter. Let me start with the basics. What is an asteroid? An asteroid is a small rocky body orbiting the sun. The definition is somewhat arbitrary. Anything smaller than a planet, but larger than a meteoroid, is called an asteroid. The distinction between asteroid and meteoroid is based on size. Meteoroids are smaller than 10 meters across. Asteroids are larger. When an asteroid enters Earth's atmosphere and becomes visible as a streak of light, it's called a meteor. If it survives the journey through the atmosphere and hits the ground, It's called a meteorite. So the same object can have three different names depending on where it is and what's happening to it. That's confusing, but it's the terminology astronomers use. Asteroids vary tremendously in size and composition. The smallest known asteroids are a few meters across. The largest, Ceres, is 950 kilometers in diameter. That's larger than the distance from New York to Chicago. Ceres is so large and so round that it's classified as a dwarf planet, not an asteroid. Most asteroids are irregularly shaped. They're not spheres. They're lumpy, jagged, misshapen rocks. Some have moons orbiting them. Some are binary systems. Two asteroids orbiting each other. Some are contact binaries. Two asteroids touching each other, held together by their mutual gravity. The composition varies too. Some asteroids are mostly rock, silicates. Some are metallic, mostly iron and nickel. Some are carbonaceous, containing carbon compounds and water. The composition of an asteroid tells you about where it formed in the early solar system. Now here's the question that gets at the heart of the story. Where do asteroids come from? For a long time, astronomers believed that asteroids were the remnants of a planet that had been destroyed. They theorized that a planet had orbited where the asteroid belt is now, and something had caused it to explode, leaving behind the asteroids as fragments. This theory made intuitive sense. You have this gap in the solar system between Mars and Jupiter where no planet orbits. You have millions of asteroids in that region. Maybe those asteroids were once a planet, but in the 1970s, astronomers calculated the total mass of all asteroids in the asteroid belt, and they made a surprising discovery. There isn't nearly enough mass. If you gathered all the asteroids in the asteroid belt and combined them, the total mass would be less than the Moon. It would be a body maybe 1,500 kilometers in diameter. That's not a destroyed planet. That's way too small. So the asteroids didn't come from a destroyed planet. Something else was going on. The correct explanation came from studying planetary formation and understanding the early solar system. Remember from the previous discussion, the solar system formed from a collapsing nebula about 4.6 billion years ago. The disk of gas and dust around the young sun gradually coalesced into planets through a process called accretion. Dust particles collided and stuck together, forming larger and larger bodies. Eventually, these bodies were massive enough to gravitationally attract more material, accelerating the accretion process. In the region where the asteroid belt is now, this process was interrupted. Jupiter formed in the outer solar system, and it's massive, about 318 times the mass of Earth. Because of its size, Jupiter's gravity was incredibly strong, and because of orbital resonances and gravitational interactions, Jupiter's gravity stirred up the asteroid-forming region. It injected energy into the orbits of the planetesimals, the small bodies that were supposed to coalesce into a planet. This stirring had a dramatic effect. Instead of the planetesimals colliding gently and sticking together to form a larger body, they were given enough velocity that when they collided, they shattered instead of merging. Collisions became destructive rather than constructive. Additionally, Jupiter's gravity scattered some of the planetesimals out of the asteroid belt region entirely. Some were ejected into the inner solar system, some were thrown into the outer solar system. The result, no planet formed in the asteroid belt region. Instead, you have millions of leftover planetesimals, asteroids, in scattered orbits. This is called the grand tack model, though there are variations. It explains why the asteroid belt is so sparse, why there's no planet there, and why asteroids are what they are. The building blocks of planets that never got assembled. Now, this explanation raises a fascinating question. What if Jupiter hadn't formed? Or what if Jupiter had formed slightly differently? If Jupiter hadn't stirred up the asteroid belt, then the asteroids probably would have coalesced into a planet. Maybe not a massive planet, the total mass isn't enough for that, but a planet perhaps similar in size to Mars or smaller. If that planet had formed, the asteroid belt wouldn't exist as it does now. There would be fewer objects available to impact Earth. There would be fewer extinction events caused by asteroid impacts. In other words, Jupiter's presence, or more specifically, Jupiter's gravitational influence on the asteroid belt, is directly responsible for the existence of asteroids as we know them. And that has profound implications for Earth's history, because asteroids have periodically collided with Earth and caused mass extinctions. So in a sense, the dinosaurs went extinct because Jupiter stirred up the asteroid belt billions of years before the extinction event. Jupiter's gravity, millions of years earlier, set in motion the sequence of events that would eventually lead to an asteroid impact 66 million years ago. This is causality on a scale that's hard to comprehend. One planet's gravitational influence exerted over billions of years shaped the fate of species on another planet. Everything is connected. Let me tell you about the different types of asteroids, because this is where the composition and origin story really comes into focus. Asteroids are classified into several categories based on their reflectivity and spectral characteristics. The three main categories are C-type asteroids, carbonaceous. These are the most common, making up about 75% of known asteroids. They're dark and contain carbon compounds, water, and organic molecules. They formed in the outer parts of the asteroid-forming region, where it was cold enough for water and volatiles to condense. S-type asteroids, silicate. These make up about 17% of known asteroids. They're brighter and composed mostly of silicate minerals and some metal. They formed closer to the sun than C-types, in warmer regions where water couldn't condense. M-type asteroids, metallic. These make up about 8% of known asteroids. They're composed mostly of iron and nickel. They're thought to be the exposed cores of differentiated bodies, asteroids that were large enough and hot enough to separate into a metal core and rocky mantle, but were then fragmented by collisions. The distribution of these types across the asteroid belt tells a story. The C-type asteroids are more common in the outer asteroid belt. The S-type asteroids are more common in the inner asteroid belt, and the M-type asteroids are scattered throughout. This distribution reflects the temperature gradient in the early solar system. It was hotter closer to the sun, cooler farther away. Different materials condensed at different temperatures, and the asteroids we see today are the remnants of those early condensations. In other words, asteroids are like a geological record of the early solar system's chemistry. By studying their composition, we're literally reading the history of planetary formation written in stone. Now, I want to talk about something that's genuinely profound: the largest asteroids and what they tell us about planetary formation. The largest asteroid series is special. It's so large that it's classified as a dwarf planet. It has a diameter of 950 kilometers. It's round, not irregular like most asteroids, and it contains about 25% of the total mass of the entire asteroid belt. Ceres is thought to be a planetary embryo, a protoplanet that almost became a planet but was prevented from growing further by Jupiter's gravitational influence. It formed in the asteroid belt region, accumulated material, grew to planetary size, but then Jupiter's stirring disrupted the disk and prevented further accretion. The next largest asteroids, Vesta, Pallas, and Juno, are significantly smaller than Ceres. Vesta is about 525 kilometers in diameter. Pallas is about 510 kilometers. Juno is about 250 kilometers. After that, there's a steep drop-off. The next largest asteroids are only a few hundred kilometers across, or smaller. This size distribution is revealing. It suggests that the asteroid belt once had a few large bodies, planetary embryos, that were in the process of coalescing. But Jupiter's gravity disrupted this process, and these embryos were never able to merge into a full planet. If the asteroid belt had been allowed to evolve peacefully, without Jupiter's interference, it might have produced one or more planets. We don't know what those planets would have been like, but they would have fundamentally changed the structure of the inner solar system. Let me tell you about something called the Nice model. Pronounced nice like the city in France, not like the adjective, because it's revolutionized our understanding of the early solar system and the asteroids. For decades, astronomers assumed that the planets formed in roughly their current positions and then stayed there. Jupiter formed in the outer solar system and orbited there. Saturn formed beyond Jupiter and orbited there, and so on. But in the 2000s, a group of astronomers from the University of Nice in France proposed something radical. The planets didn't stay where they formed. They migrated. They moved around significantly in the first few 100 million years of the solar system's existence. In the Nice model, Jupiter and Saturn started closer to the Sun than they are now. Over time, gravitational interactions with the disk of planetesimals caused them to migrate outward. But this migration wasn't smooth. At some point, according to the model, there was a planetary scattering event, a chaotic period where Jupiter, Saturn, Uranus, and Neptune all underwent dramatic orbital changes. During this scattering event, Jupiter and Saturn moved significantly. Their orbits became more eccentric. They scattered planetesimals throughout the solar system. Some planetesimals were ejected entirely. Some were thrown into the inner solar system, where they impacted the terrestrial planets. This chaotic period is called the Late Heavy Bombardment, and it lasted from roughly 4.1 to 3.8 billion years ago, a few 100 million years after the solar system formed. The Nice model explains several things. Why the asteroid belt is so sparse. Jupiter scattered planetesimals out. Why there are asteroids beyond Neptune in the Kuiper belt. Why the moon has so many large impact craters from bombardment during this period, and why there's evidence of a late period of intense asteroid impacts on Earth. In other words, the asteroids we see today, both in the asteroid belt and elsewhere, are the remnants of a catastrophic rearrangement of the entire solar system. They're debris from a giant cosmic collision that happened billions of years ago. Now, let me tell you about something that connects asteroids to you directly: meteorites. Meteorites are asteroids that have collided with Earth and made it through the atmosphere to land on the surface. And meteorites are incredibly valuable because they're samples of material from the early solar system. The oldest meteorites we have are 4.56 billion years old, older than Earth itself. How is that possible? Because they formed in the solar nebula before Earth was fully assembled. They're pristine samples of the material that formed the solar system. By analyzing meteorites, we can determine the composition of the early solar system. We can measure isotope ratios that tell us about nuclear processes in dying stars before our solar system formed. We can find organic molecules, the building blocks of life, preserved in carbonaceous meteorites. Some meteorites contain tiny grains of material that predate the solar system. These grains, formed in other star systems billions of years ago, were incorporated into the solar nebula and have been preserved in meteorites ever since. We're literally holding pieces of other stars in our hands. Meteorites also give us information about planetary differentiation, the process by which planets separated into a metal core and a rocky mantle. Iron meteorites are thought to be the cores of differentiated asteroids. Stony iron meteorites are thought to be material from the boundary between the core and mantle. By studying these, we can understand how planets formed and evolved. And meteorites tell us about the age of the solar system. By measuring radioactive decay in meteorites, we can precisely determine when the solar system formed. The answer is 4.567 billion years ago, give or take a few million years. That precision is remarkable, and it comes from studying meteorites. Let me talk about asteroid impacts and their role in Earth's history, because this is where asteroids become intensely relevant to us. The most famous asteroid impact in human-relevant timescales is the Chicxulub impact, which occurred 66 million years ago. An asteroid roughly 10 kilometers in diameter collided with Earth near the Yucatan Peninsula in what is now Mexico. The impact released energy equivalent to billions of nuclear bombs. It created a crater 180 kilometers wide. It triggered global wildfires, earthquakes, and a tsunami. But the most catastrophic effect was the atmospheric dust. The impact vaporized rock and sent it high into the atmosphere. Dust and sulfur aerosols blocked out the sun. Photosynthesis stopped. Temperatures plummeted. Food chains collapsed. This is the extinction event that killed the dinosaurs. About 75% of all species went extinct. The dinosaurs, which had dominated Earth for 165 million years, were wiped out in geological instant. But here's what's crucial. If that asteroid hadn't impacted Earth, dinosaurs would still be here. Humans would never have evolved. Mammals would probably still be small, insignificant creatures hiding in the shadows of dinosaurs. Your existence depends on an asteroid impact 66 million years ago. Without that impact, you wouldn't exist. This is staggering. This is the kind of fact that should make you reconsider your place in the universe. Your consciousness, your thoughts, your very existence is contingent on a random collision between Earth and a piece of rock that happened long before your species even existed. And it's not just this one impact. There have been multiple mass extinction events in Earth's history, and many are thought to be related to asteroid impacts. The extinction event 252 million years ago, the Permian-Triassic extinction that killed 96% of marine species, might have been triggered by asteroid impacts. Asteroids have been shaping Earth's history for billions of years. They've determined which species survive and which go extinct. They've sculpted the biosphere. And they continue to be a potential threat today. Speaking of present-day threats, let me talk about near-Earth asteroids, NEAs. A near-Earth asteroid is an asteroid whose orbit brings it close to Earth's orbit. There are thousands of known NEAs, and astronomers estimate that there are probably tens of thousands more that haven't been discovered yet. Most NEAs are harmless. They pass near Earth but don't collide. But some are on collision courses. And if one collides with Earth, the consequences depend on the size of the asteroid. A small asteroid, a few meters across, will burn up in the atmosphere and pose no threat. An asteroid 10 meters across might impact the ground and create a crater, but wouldn't cause global catastrophe. An asteroid 100 meters across would create significant regional damage. An asteroid 1 kilometer across would cause global climate effects and potential mass extinction. Fortunately, large asteroids are relatively rare. The probability of a 1 kilometer asteroid impacting Earth in any given year is roughly 1 in 500,000. But that probability, played out over millions of years, becomes significant. Over human timescales, thousands of years, it's still relatively unlikely, but not impossible. What's more certain is that smaller asteroids will impact Earth. On average, an asteroid about 4 meters across impacts Earth's atmosphere roughly once a year. Most burn up. Some create impressive fireballs. Occasionally, one makes it to the ground. The Chelyabinsk meteor, which exploded over Russia in 2013, was roughly 20 meters across. It released energy equivalent to 400 kilotons of TNT, about 30 times the energy of the Hiroshima bomb. It flattened 80 million trees. If it had impacted a populated city instead of a remote area, it would have killed hundreds of thousands of people. And it wasn't detected until after it impacted. We didn't see it coming. This is the reality of asteroid impacts. We're vulnerable. Earth is vulnerable. Civilization is vulnerable. And while large extinction-level impacts are rare on human timescales, they're not impossible. Now, this raises a question that's increasingly relevant. What can we do about asteroids? In recent years, space agencies have been developing asteroid detection and deflection technology. NASA's Planetary Defense Coordination Office tracks near-Earth asteroids and calculates their trajectories. If an asteroid is found to be on a collision course with Earth, scientists have developed techniques to deflect it. The simplest technique is called a kinetic impact. You send a spacecraft to collide with the asteroid. The impact transfers momentum, slightly changing the asteroid's trajectory. If done early enough, years or decades before the potential impact, a small change in trajectory can mean the difference between a miss and a collision. In 2022, NASA tested this technique with the DART mission, a double asteroid redirection test. A spacecraft was intentionally crashed into an asteroid called Dimorphos. The impact successfully changed the asteroid's orbit. Other deflection techniques have been proposed, using nuclear explosions to nudge an asteroid, using gravity tractors, spacecraft that fly near an asteroid and use their own gravity to pull it, using solar sails to redirect an asteroid over long timescales. The point is, we have the technology to defend Earth against asteroid impacts. We might not be perfect at it yet, but we're developing the capability. We're not helpless victims of cosmic chance. But this requires international cooperation, funding, continued research, and political will. It's not guaranteed that we'll implement these systems effectively. Let me tell you about something called the Yarkovsky effect, because it's a fascinating example of how seemingly small forces can have large effects over time. The Yarkovsky effect is a small force exerted on asteroids by sunlight. Here's how it works. Sunlight heats one side of an asteroid. That side radiates heat. But the heated side doesn't radiate instantly. There's a thermal lag. So by the time the side has rotated to face away from the sun, it's still radiating heat. This creates a tiny thrust, a minuscule force pushing the asteroid. It's incredibly small, but it's constant. Over millions of years, this tiny force accumulates and can significantly change an asteroid's orbit. This might seem irrelevant. It's such a small force, but it has profound implications. The Yarkovsky effect can push asteroids from stable orbits into orbits that bring them closer to Earth. It can push asteroids from orbits in the asteroid belt into the inner solar system. In other words, the Yarkovsky effect is a mechanism by which asteroids can gradually migrate toward Earth over millions of years. Some of the near-Earth asteroids we observe today might have been pushed into their current dangerous orbits by the Yarkovsky effect. This is a beautiful example of how physics works on different scales. You have the massive gravitational force of planets pulling on asteroids. But you also have the minuscule thermal force of sunlight pushing on asteroids. Both matter, both shape the history of the solar system. Now, I want to talk about asteroid mining because it's becoming increasingly relevant as technology advances. Asteroids contain valuable resources, metals like iron, nickel, cobalt, platinum. Some asteroids contain more platinum than has ever been mined on Earth. Water ice in some asteroids could be used as fuel or for drinking water on future space stations. For decades, asteroid mining was pure science fiction. But with advances in robotics, autonomous systems, and space launch technology, it's becoming increasingly feasible. Several companies are now developing the technology to mine asteroids. The process would involve detecting an asteroid, characterizing it, sending a spacecraft to it, extracting material, and returning the material to Earth, or using it in space for construction or fuel. The economics are still uncertain. It's not clear whether asteroid mining will be profitable, but if it is, the implications are enormous. Asteroid mining could provide resources that would make space exploration much cheaper. It could reduce the need for mining on Earth with all its environmental consequences, but it also raises fascinating questions. Who owns asteroids? International space law says that no country can claim ownership of a celestial body. But what about individual companies or nations that extract resources? This is going to be a crucial legal and political question in the coming decades. Let me tell you about something called Ryugu and Bennu, because these are asteroids we've actually visited and collected samples from, and the results are revolutionary. Ryugu is a small asteroid, about 900 meters in diameter. In 2018, the Japanese spacecraft Hayabusa 2 arrived at Ryugu and collected samples from its surface. It returned those samples to Earth in 2020. Scientists have been analyzing those samples ever since. Similarly, Bennu is a small asteroid about 500 meters in diameter. In 2020, the American spacecraft OSIRIS-REx collected samples from Bennu and is returning them to Earth. Arrival in 2023. What have we learned from these samples? Several remarkable things. First, these asteroids contain water. Not ice, but water locked into mineral structures. This tells us that water was present in the asteroid belt in the early solar system, even at these relatively small bodies. Second, these asteroids contain organic molecules, complex carbon-based compounds. Some of these molecules are amino acids, the building blocks of proteins. Some are other organic compounds not found in living things. This tells us that asteroids were chemical laboratories in the early solar system, synthesizing organic compounds through non-biological processes. Third, the samples show evidence of aqueous alteration, chemical reactions that occurred when liquid water was present in these asteroids. This indicates that these asteroids were heated early in their existence, probably by radioactive decay of short-lived isotopes. Fourth, the age of these materials confirms that they formed early in the solar system's history, probably within the first few million years. In other words, these samples are telling us that asteroids were dynamic, chemically active bodies in the early solar system. They weren't just inert rocks floating in space. They were chemical factories. And here's something profound. Some scientists believe that the organic compounds delivered to Earth by asteroids and comets might have played a role in the origin of life. The building blocks of life might have come from space, delivered by these ancient asteroids. Let me explore that idea more deeply because it connects asteroids to the fundamental question of life's origin. The hypothesis is called panspermia, the idea that life, or the chemical precursors of life, originated in space and was delivered to Earth by meteorites and comets. This might sound far-fetched, but there's evidence for it. Meteorites contain amino acids and other organic compounds. Comets contain organic compounds, and experiments have shown that organic compounds can form through abiotic chemical reactions in space, reactions not involving life. If this is true, then life on Earth didn't originate purely in Earth's oceans or atmosphere. At least some of the chemical building blocks of life came from space. This doesn't solve the problem of life's origin, it just pushes it back. Instead of asking how life originated on Earth, you're now asking how life originated somewhere in space. But it does suggest that the chemistry of life is universal. The same chemical processes that created organic compounds on Earth also occurred in asteroids and comets throughout the solar system. And if organic compounds are universal, if they form naturally whenever you have the right chemical conditions, then the implication is that life might also be universal. Life might have emerged on countless worlds throughout the galaxy, not just on Earth. This is speculative. We don't have evidence of life elsewhere, but asteroids give us a hint that the chemistry of life is common in the cosmos. Now let me talk about something that's been bothering astronomers for decades: the asteroid belt's mass deficit. The asteroid belt today contains maybe 4% of the mass of the Moon. But based on how many asteroids we observe and their composition, scientists can estimate how much mass the asteroid belt should contain if it had never been disrupted. The calculations suggest that the early asteroid belt should have contained maybe 100 times more mass than it does today. So where did all that mass go? The answer is it was scattered. When Jupiter formed and stirred up the asteroid belt, it injected energy into the planetesimals' orbits. Some planetesimals were ejected entirely from the solar system. Some were scattered into the inner solar system, where they collided with the terrestrial planets. Some were scattered into the outer solar system, becoming part of the Kuiper belt and beyond. This scattering event had profound consequences. It explains why the terrestrial planets, Mercury, Venus, Earth, Mars, received a late heavy bombardment of asteroids and comets. It explains why the Moon was heavily cratered. It explains the current structure of the solar system. But it also raises a fascinating question. What if Jupiter had scattered things differently? What if more or fewer planetesimals had been ejected? What if the scattering had happened at a different time? The early solar system was chaotic. Small changes in initial conditions would have led to vastly different outcomes. We could have ended up with a very different planetary configuration. We could have ended up with more or fewer terrestrial planets. Earth might not exist at all. Or if it did, it might be in a different location with a different mass. In other words, the specific arrangement of planets we observe today, including Earth's existence and its particular location in the habitable zone, is contingent on the specific way Jupiter scattered planetesimals billions of years ago. This is cosmic chance on a profound scale. We exist because of a random scattering event in the early solar system. Let me tell you about the Kirkwood gaps, because they're a beautiful example of how orbital mechanics shapes the asteroid belt. If you plot the number of asteroids as a function of their orbital period, or equivalently, their semi-major axis, their average distance from the Sun, You don't see a smooth distribution. Instead, you see gaps. Certain orbital periods have very few asteroids. Other orbital periods have many asteroids. These gaps are called Kirkwood gaps, named after the astronomer who discovered them in the 1860s. They occur at specific orbital periods that have a simple mathematical relationship to Jupiter's orbital period. For example, there's a gap at 2.5 astronomical units from the Sun. Asteroids at this distance have an orbital period that's exactly 3 to 1 with Jupiter's orbital period, meaning they complete 3 orbits for every 1 orbit Jupiter completes. Why is this a gap? Because of orbital resonance. When an asteroid's orbital period has a simple ratio with Jupiter's orbital period, they encounter Jupiter at the same point in their orbits repeatedly. Each encounter gives the asteroid a small gravitational kick. Over millions of years, these kicks accumulate and destabilize the asteroid's orbit. Asteroids in resonance with Jupiter are either ejected from the asteroid belt or moved to different orbits. The result is a gap, a region where asteroids don't typically exist. This is another example of how Jupiter's gravity shapes the asteroid belt. It's not just about stirring up the early planetesimals. It's about ongoing long-term gravitational interactions that continue today. Now let me talk about binary asteroids and contact binaries because they're some of the most fascinating objects in the solar system. Some asteroids have companions, smaller asteroids orbiting them. These are called binary asteroids. The primary asteroid might be a few hundred kilometers across, with a secondary asteroid a few tens of kilometers across, orbiting at a distance of thousands of kilometers. Even more interesting are contact binaries. 2 asteroids orbiting so close that they're actually touching. They're in contact with each other, held together by their mutual gravity. From a distance, they look like a single potato-shaped object, but up close, you can see that they're 2 distinct bodies touching along their surfaces. How do binary and contact binaries form? There are several theories. One possibility is that a large asteroid was impacted and fractured, but the fragments didn't have enough velocity to escape each other's gravity, so they remained bound. Another possibility is that 2 asteroids came together and ended up in a bound orbit rather than colliding. Contact binaries are particularly interesting because they're on the verge of falling apart. If they rotate too fast, the centrifugal force will overcome the gravitational force holding them together, and they'll separate. If they're struck by another asteroid, they might fragment entirely. Some asteroids are even weirder. Bennu, which we discussed earlier, is a contact binary that's slowly coming apart. It's rotating so fast that material is being ejected from its surface. Over time, the 2 lobes of the contact binary might separate completely. These exotic asteroid morphologies tell us that asteroids are dynamic. They're not static rocks. They're active bodies, constantly changing, interacting gravitationally with each other and with planets. Let me tell you about something called the P/T transition asteroid hypothesis, because it's one of the most speculative ideas about asteroid impacts. The P/T transition, the Permian-Triassic transition, happened 252 million years ago. It's the most severe mass extinction event in Earth's history. About 96% of marine species went extinct. About 70% of terrestrial vertebrate species went extinct. The extinction was so severe that it's called the Great Dying. For decades, scientists weren't sure what caused the P/T extinction. There was evidence of massive volcanic activity in Siberia. There was evidence of climate change. There was chemical evidence of oxygen depletion in the oceans. But in recent years, some scientists have proposed that an asteroid impact also played a role. An asteroid might have collided with Earth around the time of the PT extinction, contributing to the global catastrophe. The evidence is debated and not universally accepted. No PT impact crater has been definitively identified, though there are candidates. But if true, it would mean that Earth has experienced at least two extinction-level asteroid impacts in its history. The P/T impact 252 million years ago, and the Chicxulub impact 66 million years ago. This raises a sobering thought. If Earth has been hit twice, it will probably be hit again. It's not a question of if, but when. Now let me talk about something more hopeful: how we're mapping and monitoring near-Earth asteroids. In 1998, NASA set a goal to find and track 90% of near-Earth asteroids larger than 1 kilometer. This goal was met in 2011. We now know the positions and trajectories of most of the large asteroids that could cause global catastrophe. But there are still many smaller asteroids we haven't found. In 2005, NASA set a new goal to find 90% of near-Earth asteroids larger than 140 meters by 2020. This deadline was extended to 2030, but it's still a work in progress. Finding these asteroids requires telescopes, both ground-based and space-based. Ground-based telescopes scan the night sky looking for moving objects. Space-based telescopes like NEOWISE observe infrared radiation from asteroids, which helps determine their size and composition. Once an asteroid is discovered, its trajectory is calculated. This calculation is quite precise. Astronomers can predict an asteroid's position years in advance. If the calculation shows that an asteroid will collide with Earth, the alarm is raised. So far, no large asteroid has been discovered on a collision course with Earth in the foreseeable future, the next century or so. But smaller asteroids continue to be discovered, and some do have orbits that bring them close to Earth. The detection and tracking systems are improving. Better telescopes are being built. More systematic surveys are being conducted. Over time, we'll have a more complete picture of the asteroid population and be able to predict potential impacts with increasing accuracy. Let me tell you about the asteroid that almost hit Earth in 2029, Apophis. Apophis is a near-Earth asteroid about 370 meters in diameter. When it was first discovered in 2004, calculations suggested it might collide with Earth on April 13, 2029. There was a brief period of concern in the scientific community, but as more observations were made, the calculations were refined. It became clear that Apophis would miss Earth in 2029, passing about 30,000 kilometers away, closer than some satellites orbit, but not on a collision course. However, Apophis will pass so close to Earth that Earth's gravity will affect its trajectory. This gravitational interaction will alter Apophis's orbit. And while it won't hit Earth in 2029, this close encounter could potentially set it up for a collision on a future pass. Current calculations suggest that a collision is unlikely, but not impossible. Apophis will continue to be monitored. But here's what's interesting. The near miss in 2029 will be an incredible opportunity for scientists. Apophis will be bright enough to see with the naked eye. It will be the closest approach of a large asteroid in recorded history. Space agencies are planning to send spacecraft to observe it and possibly to land on it and collect samples. So what could have been a catastrophe is instead a scientific opportunity. We'll get to study a near-Earth asteroid up close and learn about its composition, structure, and trajectory. Now let me connect asteroids back to life on Earth and what their study tells us about our place in the universe. Asteroids are ancient. Many are older than Earth. They're samples of the material that form the solar system. By studying them, we're reading the history of our cosmic origins. Asteroids have shaped life on Earth. The extinction of the dinosaurs was caused by an asteroid impact. Without that impact, we wouldn't exist. Every extinction event, every adaptive radiation, every major transition in Earth's history has been influenced by asteroid impacts. Asteroids are a threat to our future. We live under the constant shadow of potential asteroid impacts. A sufficiently large asteroid could end human civilization. This isn't hypothetical. It's real and inevitable on geological timescales. But asteroids also offer opportunity. They contain resources we might mine. They contain scientific information that teaches us about the solar system. They're laboratories of chemistry and physics accessible within our technological reach. And studying asteroids forces us to confront questions about our place in the cosmos. We're not the center of the universe. We're not immune to cosmic forces. We're one species on one planet orbiting one star in one galaxy among billions. And our fate is intertwined with the fate of rocks floating in space. This should humble us, but it should also inspire us, because we've reached a point in our technological development where we can study these rocks. We can predict their trajectories. We can potentially deflect them. We're developing the capability to protect ourselves from cosmic hazards. This is remarkable. This is something no other species on Earth has achieved. We're becoming a spacefaring civilization. We're taking responsibility for our future. Let me end with something that ties this all together: the cosmic perspective that asteroids provide. When you look up at the night sky, you see stars, you see planets, but you don't see asteroids. They're too small and too distant and too dark, but they're there, millions of them, each one a fragment of planetary formation, each one a story of creation and destruction in the early solar system. And one of them, billions of years ago, collided with Earth and killed the dinosaurs, allowing mammals to flourish, allowing humans to evolve, allowing you to exist. You are made of star stuff, as Carl Sagan said, but you're also made of asteroid stuff. The metals in your body, the elements in your cells, came from asteroids that collided with Earth in the late heavy bombardment. You are quite literally made of asteroids. Your existence is tied to their existence. Your history is their history. And as we move into the future, asteroids will continue to be important. They might threaten us. They might resource our expansion into space. They might teach us fundamental truths about the cosmos. The story of asteroids is the story of the solar system. It's the story of planetary formation and cosmic violence and the delicate balance between creation and destruction. It's the story of how we came to be here and what might happen next. Every few years, if you know where to look, you can see something remarkable in the night sky. A fuzzy ball with a long tail stretching across the heavens. It's a comet. And for thousands of years, humans have watched comets with a mixture of wonder and dread, not knowing what they were or where they came from. We now know that comets are icy bodies from the outer solar system, remnants of planetary formation, visitors from the deep, cold regions beyond Neptune. We know their composition. We know their trajectories. We've sent spacecraft to intercept them and collect samples. But comets are still mysterious. They're unpredictable. Some appear exactly when we expect them. Others surprise us by brightening unexpectedly or fading faster than predicted. Some are beautiful. Some are subtle. Some will never return to the inner solar system. And comets tell us something profound about the structure of the solar system and the origin of water and organic compounds on Earth. This is the story of comets, what they are, where they come from, and why they matter. Let me start with basics. What is a comet? A comet is a small icy body orbiting the sun. When a comet is far from the sun, in the cold regions of the outer solar system, it's essentially a dirty snowball, a mixture of ice, water ice, methane ice, ammonia ice, carbon dioxide ice, and dust and rock. But as a comet approaches the sun, something remarkable happens. The ice begins to sublime, to evaporate directly from solid to gas without becoming liquid. This creates a cloud of gas and dust around the comet's nucleus, the solid core. This cloud is called the coma. The coma can be enormous, sometimes larger than the sun itself, but it's incredibly tenuous. It's mostly empty space with gas and dust particles spread thinly throughout. As the comet gets closer to the sun, the solar wind, the stream of charged particles flowing outward from the sun, begins to push on the coma. This creates the tail. The tail always points away from the sun, regardless of the comet's direction of motion. So as a comet approaches the sun, its tail points backward. As it recedes, the tail points forward. The tail can be spectacular. Some comets have tails stretching millions of kilometers across space. The Great Comet of 1811 had a tail so large that Earth actually passed through it. People worried that the tail might be toxic. It wasn't, but the fear was real. Now here's a question that's been puzzling astronomers for centuries. Where do comets come from? For a long time, it was thought that comets came from outside the solar system, that they were interstellar visitors wandering through space and occasionally passing near the sun. This seemed plausible because comet trajectories appeared to be parabolic or hyperbolic, suggesting that comets came from infinity and returned to infinity. But in the 1950s, an astronomer named Jan Oort proposed something different. He theorized that there was a vast spherical shell of icy bodies surrounding the solar system. These bodies, he proposed, were comets. They orbited the sun at enormous distances in the deep cold of space beyond Pluto. Oort's reasoning was mathematical and elegant. He calculated that there should be a source of comets at a distance of about 100,000 astronomical units from the sun. An astronomical unit is the Earth-Sun distance, about 150 million kilometers. At this distance, the solar system's gravity is still strong enough to bind these objects, but weak enough that they can be perturbed by passing stars. When a nearby star passes through the solar system, its gravity can nudge a comet's orbit slightly. This nudge might send a comet into the inner solar system, where it becomes visible as it approaches the sun. Or it might nudge a comet outward into an even more distant orbit. This structure, a vast spherical shell of comets surrounding the solar system, came to be called the Oort cloud. The Oort cloud is hypothetical. We've never directly observed it. It's too far away and too dark. But its existence is strongly suggested by the distribution and properties of known comets. The Oort cloud is estimated to contain hundreds of billions of comets, maybe trillions. No one knows for sure. But the total mass is thought to be several times the mass of Earth. The cloud is divided into two regions. The outer Oort cloud, at distances of 100,000 to 200,000 astronomical units, and the inner Oort cloud, at distances of 2,000 to 100,000 astronomical units. The inner Oort cloud is sometimes called the Hills cloud, named after the astronomer Jack Hills, who studied it extensively. From Earth's perspective, the Oort cloud is incomprehensibly distant. The nearest star, Proxima Centauri, is about 4.2 light years away, or about 270,000 astronomical units. The Oort cloud extends from about 2,000 astronomical units to 200,000 astronomical units, So it's relatively close compared to the nearest star, but vastly more distant than anything else in the solar system. The light travel time to the Oort cloud would be months. A spacecraft traveling at current speeds would take thousands of years to reach it. We will never directly observe the Oort cloud with our current technology. Now, let me tell you about the other source of comets, the Kuiper Belt. The Kuiper Belt is a region of icy bodies orbiting the Sun beyond Neptune. It extends from about 30 astronomical units, Neptune's orbit, to about 55 astronomical units from the Sun. It's much closer than the Oort cloud, much more accessible, and we've actually observed many objects in it. The Kuiper Belt contains hundreds of thousands of icy bodies larger than 100 kilometers across. Pluto is the largest known object in the Kuiper Belt, though it was reclassified as a dwarf planet in 2006. Other notable objects include Eris, Makemake, and Haumea. Comets from the Kuiper Belt typically have orbital periods of less than 200 years. They orbit in roughly the same plane as the planets. They have relatively gentle orbits. They're not on extreme parabolic trajectories from the Oort cloud. Comets from the Oort cloud, by contrast, typically have very long orbital periods, thousands or millions of years, or orbits that are parabolic or hyperbolic. They come from random directions approaching the ecliptic plane at steep angles. So by observing a comet's trajectory and orbital period, astronomers can often determine whether it came from the Kuiper Belt or the Oort cloud. Let me tell you about some famous comets and what makes them special. Halley's Comet is probably the most famous comet. It appears every 75 to 76 years. It was observed in 240 BC by Chinese astronomers. It appears in the Bayeux Tapestry, which depicts events from 1066. Edmund Halley, an English astronomer, realized that comets observed in 1531, 1607, and 1682 were actually the same comet returning periodically. He predicted it would return in 1758, and it did, after his death. The comet is now named after him. Halley's Comet is relatively bright and accessible. When it appears, it can be seen with the naked eye from Earth. Its last appearance was in 1986. Its next appearance will be in 2061. Comet Hale-Bopp appeared in 1997 and was one of the brightest comets in the last century. It was visible to the naked eye for over a month. It was widely observed, widely photographed, and widely celebrated. Its orbit has a period of about 2,533 years, meaning it won't return until around 4,385. Comet Hyakutake appeared in 1996 and was an unexpected brightener. It wasn't expected to be visible to the naked eye, but it surprised astronomers by brightening significantly. It passed within 15 million kilometers of Earth, relatively close in astronomical terms. Comet Neowise appeared in 2020 and was visible to the naked eye in the northern hemisphere. It was bright enough that people could see it without optical aid. It provided a beautiful display of what a comet looks like when illuminated by the sun. Now let me tell you about some obscure and fascinating comets that don't get as much attention. Comet 67P/Churyumov-Gerasimenko is famous not for its brightness, but for being visited by a spacecraft. The European Space Agency's Rosetta spacecraft arrived at this comet in 2014 and orbited it for 2 years, collecting detailed data and images. The images revealed that the comet has a bizarre rubber duck or peanut shape. It's actually a contact binary, 2 lobes touching each other. The comet's surface was found to have cliffs, boulders, and flat regions. Organic molecules were detected on the surface. The Rosetta mission also deployed a lander called Philae onto the comet's surface. Philae bounced multiple times before coming to rest in a shadowed area. It conducted several experiments before its battery died. But in that brief time, it revolutionized our understanding of comets. Comet Shoemaker-Levy 9 is famous for a catastrophic event. This comet was discovered in 1993, orbiting Jupiter. It had been captured by Jupiter's gravity. Astronomers calculated that the comet would collide with Jupiter in 1994. And it did. The collision was spectacular. The comet had fragmented into about 20 pieces, and each piece impacted Jupiter in sequence. The impacts created dark scars on Jupiter's atmosphere that were visible for months. It was the first time humans had observed a collision between two solar system bodies, not counting asteroids impacting Earth, which happened in the past but wasn't observed in real time. This event was catastrophic for the comet, but mere cosmic weather for Jupiter. But it demonstrated something important. Comets can collide with planets, and the consequences can be severe. Comet Ikea-Seki appeared in 1965 and became the brightest comet in nearly 400 years. It was so bright it was visible in daylight. Its tail stretched across much of the sky. It was seen by millions of people, and then it faded quickly. It's one of the most documented bright comets in history. Comet Holmes had an unusual outburst in 2007. Normally, Comet Holmes was a faint object, visible only through telescopes. But in October 2007, it suddenly brightened by a factor of about 1 million. It became visible to the naked eye. Astronomers believe that an impact or thermal stress caused part of the comet to fragment, suddenly increasing its surface area and reflectivity. The brightening was temporary. The comet faded again within weeks, but it was a dramatic example of how unpredictable comets can be. Let me talk about comet nomenclature, because it's confusing and reflects the history of comet discovery. Comets are named after their discoverer or discoverers. For example, Halley's Comet is named after Edmund Halley, the astronomer who identified it as a periodic comet. Hale-Bopp is named after Alan Hale and Thomas Bopp, two astronomers who independently discovered it. But comets are also given a designation based on their discovery. The designation consists of the year of perihelion, closest approach to the Sun, a letter indicating the half month of discovery, and a number indicating the order of discovery in that half month. For example, Comet C/2020 F3, Neowise means C indicates it's a non-periodic comet, P indicates periodic, 2020 is the year, F3 means it was discovered in the first half of June and was the third comet discovered in that period, and Neowise is the name of the discovery program. This nomenclature system is somewhat arcane and confuses most people, but it's standardized, and it allows astronomers to unambiguously refer to specific comets. Now let me talk about what comets are made of, because it's genuinely fascinating. Comets are composed of ices and dust. The ices include water ice, the most abundant component, methane ice, frozen methane, ammonia ice, frozen ammonia, carbon dioxide ice, frozen CO2, dry ice, other volatile ices, including compounds of nitrogen, sulfur, and other elements. The dust component includes silicate minerals, similar to sand or rock, sulfur, organic compounds, and metals. The exact composition varies from comet to comet, but all comets have this basic structure: a solid nucleus made of ice and dust, surrounded by a coma of gas and dust when active near the Sun. What's remarkable is that comets are pristine samples of the early solar system. They've been frozen in the cold outer regions since the solar system formed 4.6 billion years ago. They haven't undergone the heat and chemical processing that terrestrial planets have. They're time capsules. When we analyze comet samples, either from spacecraft visiting them or from meteorites that originated from comets, we find organic molecules, amino acids, nucleotide bases, alcohols, aldehydes, and other complex carbon compounds. Some of these molecules are the building blocks of life. In fact, some scientists believe that comets and asteroids delivered the organic compounds that eventually led to life on Earth. The hypothesis is that Earth formed too hot for complex organic molecules to survive. But comets and meteorites delivered these molecules later, after Earth had cooled. These delivered molecules then served as the chemical foundation for the origin of life. Let me tell you about comet tails because they're more complex than they appear. When you see a comet in the night sky, it looks like a single fuzzy object with a tail, but actually there are typically two tails, an ion tail and a dust tail. The ion tail, also called the plasma tail, is composed of gas, primarily ionized gas that's been stripped of electrons by ultraviolet radiation from the sun. This tail is pushed by the solar wind, the stream of charged particles flowing outward from the sun. The ion tail points almost exactly away from the sun, perpendicular to the solar wind's direction. The ion tail is typically blue in color because the ionized molecules, primarily carbon monoxide, emit blue light when excited by solar UV radiation. The dust tail is composed of solid dust particles ejected from the comet's nucleus. These particles are pushed by radiation pressure from sunlight. Photons carry momentum and transfer it to dust particles. The radiation pressure is much weaker than the solar wind's effect on ions, so the dust tail curves slightly. It doesn't point exactly away from the sun. It lags behind the comet's motion. The dust tail is typically yellow or white in color because it reflects sunlight. Some comets have multiple dust tails, created as different dust particle sizes, separate due to differential radiation pressure. Comet Ikea-Seki had a particularly complex tail structure with multiple streaks. The tail of a comet is so tenuous that you could breathe the material and feel nothing. It's mostly empty space. Earth has actually passed through comet tails without any noticeable effect. Now let me tell you about periodic comets and long-period comets because the distinction is important. Periodic comets have orbital periods shorter than 200 years. They come from the Kuiper belt or from the inner Oort cloud. They return to the inner solar system regularly. We can predict their appearances with reasonable accuracy. Halley's Comet is the most famous periodic comet, with a period of about 76 years. But there are others. Comet Encke has a period of only 3.3 years and is the shortest period known periodic comet. Comet Tuttle has a period of 13.6 years. Comet Swift-Tuttle has a period of 133 years. Periodic comets are typically fainter than long-period comets because they've passed through the inner solar system many times and lost much of their volatile material. Each pass near the sun causes sublimation, slowly depleting the comet's ices. Long-period comets have orbital periods longer than 200 years, often thousands or millions of years. They come from the Oort cloud. They're on their first or early passage through the inner solar system. They're often brighter and more spectacular than periodic comets because they still have abundant volatile material. Hale-Bopp and Hyakutake are long-period comets. Comet C/1680 V1, the Great Comet of 1680, is thought to have an orbital period of about 8,500 years. Let me tell you about hyperbolic comets. Because they're bizarre and raise questions about the solar system's boundaries. Most comets have elliptical orbits. They orbit the sun and will return, eventually, even if it takes millions of years. But some comets have hyperbolic orbits. A hyperbolic orbit is not closed. It's an open parabola or hyperbola. If a comet is on a hyperbolic orbit, it will pass the sun once and then escape the solar system forever. It will never return. How can a comet end up on a hyperbolic orbit? The most likely explanation is gravitational scattering by planets. A comet might be in an elliptical orbit around the sun, but if it passes close to Jupiter, for example, Jupiter's gravity might alter the comet's orbit and change it from elliptical to hyperbolic. Some comets appear to have naturally hyperbolic orbits when first discovered, suggesting they came from interstellar space and were captured by the sun's gravity into a hyperbolic trajectory. But this is controversial. The observations might be uncertain, or the comet might have been affected by planetary gravity before we detected it. The question of whether truly interstellar comets exist is unresolved. It's possible that some comets originate outside the solar system and are just passing through. But it's difficult to prove observationally. Now let me tell you about what happens when a comet is captured by a planet's gravity. Normally, comets orbit the sun. But occasionally, a comet's trajectory brings it close to a planet. If the comet passes close enough, the planet's gravity can capture it, converting the comet's orbit from a solar orbit to a planetary orbit. Once captured, the comet orbits the planet instead of the sun. It's now a moon of the planet, technically, though a temporary one. Each time the comet orbits the planet, it experiences tidal forces, gravitational stretching caused by the planet's uneven gravity across the comet's body. These tidal forces cause stress. They heat the comet internally. They can cause fragmentation. Eventually, the comet might break apart, forming a ring system around the planet. This is thought to have happened with Saturn's rings. Saturn's rings might be the fragments of a captured comet that was torn apart by tidal forces. We've observed this process in action. Comet Shoemaker-Levy 9, which we discussed earlier, was captured by Jupiter's gravity. It orbited Jupiter briefly before colliding with the planet. The impacts released enormous energy and created visible scars on Jupiter's atmosphere. Let me tell you about outbursts and fragmentation, because they reveal the dynamic nature of comets. Comets are not static objects. They're changing constantly, especially as they approach the sun. Some comets experience sudden outbursts, sudden increases in brightness that can't be easily explained. Comet Holmes experienced a dramatic outburst in 2007, as we discussed. But outbursts happen to other comets too. One theory for outbursts is that they're caused by thermal stress. As the comet's surface heats, ice sublimates rapidly. Pressure builds up beneath the surface. Eventually, the pressure ruptures the surface, releasing a jet of gas and dust. This jet suddenly increases the comet's brightness. Another cause of outbursts might be impacts. If a small asteroid collides with a comet, it could trigger fragmentation and ejection of material. Some comets fragment entirely. Comet Biela, observed in 1826, was a single comet. When it returned in 1846, it had split into two pieces. By 1852, it had split further into at least three pieces. The comet's orbit would bring it back to Earth's region in 1859, but nothing was observed. The comet had completely disintegrated. We've observed other comets fragmenting. Comet Linear broke into multiple pieces in 2000. Comet C/2019 Y4 Atlas began fragmenting in 2020, breaking into at least 20 pieces. Comet fragmentation is unpredictable and makes predicting comet brightness difficult. A comet that's predicted to be dimly visible might suddenly brighten due to an outburst, or it might fade due to unexpected fragmentation. Let me talk about comet dust and its role in Earth's history. When a comet passes through the inner solar system, it sheds dust. This dust remains in the comet's orbit. As Earth orbits the Sun, it periodically intersects comet orbits and passes through clouds of comet dust. When Earth passes through a comet dust cloud, the dust particles enter Earth's atmosphere at high speed. They're heated by friction and create meteors, streaks of light in the night sky. We call these meteor showers. A meteor shower occurs when Earth passes through the debris stream of a specific comet. The Perseid meteor shower occurs in August and is caused by Earth passing through debris from Comet Swift-Tuttle. The Leonid meteor shower occurs in November and is caused by debris from Comet Tempel-Tuttle. Different meteor showers occur at predictable times each year because Earth's orbit is regular. Comet debris trails are predictable, so astronomers can predict when meteor showers will occur. But here's something remarkable. Comet dust that doesn't enter Earth's atmosphere falls to Earth's surface and accumulates. Over millions of years, this accumulated dust contributes to Earth's mass and composition. Some scientists estimate that Earth receives about 40,000 tons of cosmic dust per year. Over Earth's 4.6 billion year history, this adds up to a significant amount of material from space, including material from comets and asteroids. This cosmic dust carries organic compounds. It carries water. It carries the chemical building blocks of life. Some of Earth's water might have come from comets. Some of Earth's organic molecules might have come from comets. In other words, comets have been slowly seeding Earth with the materials necessary for life. Now let me tell you about the Deep Impact mission, because it's one of the most dramatic space missions ever undertaken. In July 2005, NASA intentionally crashed a spacecraft into Comet Tempel 1. The impact happened at 10.7 kilometers per second, about 38,000 kilometers per hour. The impactor was a 372-kilogram probe. The comet was icy and ancient. The collision was deliberately designed to be observed. Scientists wanted to see what happened when you smash a spacecraft into a comet. What would be ejected? What would the crater look like? The impact created a brilliant flash that was visible from Earth-based telescopes. A plume of material was ejected from the impact site. The main spacecraft, orbiting nearby, observed and photographed the plume. What scientists learned was that the comet's surface was softer than expected. Instead of blasting a clean crater, the impact created a debris plume with a composition rich in water, carbon dioxide, and organic compounds. The ejected material suggested the comet was composed of dirty ice, frozen water with dust and organic material throughout. The impact was momentous both scientifically and symbolically. We had reached out and touched a comet. We had altered a comet's orbit, though only slightly. We had proved that we could precisely navigate a spacecraft to a distant moving target and conduct an impact experiment. Let me tell you about something called the Yarkovsky effect for comets, because it affects their trajectories. The Yarkovsky effect, which we discussed with asteroids, also applies to comets. As a comet is heated by the sun, one side becomes warmer than the other. The heated side radiates thermal energy. Due to the comet's rotation, the energy radiation is slightly offset from the direction toward the sun. This creates a tiny force, the Yarkovsky effect, that slowly alters the comet's orbit. For comets, the Yarkovsky effect is combined with another effect, outgassing. As the comet sublimates, it ejects gas. This ejection of material creates a reaction force, like a rocket. The direction of this force depends on the comet's rotation and the pattern of sublimation on its surface. These forces, the Yarkovsky effect and outgassing, cause comets' orbits to change unpredictably over time. A comet's orbit calculated years in advance might be significantly different when the comet actually returns. This is why comet predictions often have large uncertainties. Now let me tell you about something fascinating: comet names in different cultures and what they meant. For most of human history, comets were mysterious and often frightening. They were interpreted as omens, signs of disaster, war, plague, or famine. In Chinese history, comets were carefully recorded and studied. The Chinese recognized that comets were recurring phenomena, not unique events. They recorded comets in their historical documents for thousands of years. Some of these ancient records allow us to trace the history of specific periodic comets. In European culture, comets were often associated with bad omens. The appearance of a comet might be interpreted as a sign that the king would die, or war would come, or plague would strike. The Great Comet of 1811 sparked fears about toxic gases in its tail. The approach of Halley's Comet in 1910 led to widespread panic. Some people believed the comet would collide with Earth or poison the atmosphere. In Islamic astronomy, comets were studied seriously as astronomical phenomena. Persian and Arab astronomers made detailed observations and calculations of comet trajectories. In modern times, comets have lost their ominous associations. They're understood as natural phenomena, but they've gained a new cultural significance. They're objects of beauty and wonder. When a bright comet appears, people gather to observe it. Comet Hale-Bopp in 1997 drew millions of observers. It inspired art, music, and literature. Comets represent the sublime, something vast, ancient, and cosmic visiting our neighborhood briefly before departing into darkness. They remind us of our smallness in the universe. Let me tell you about comet nuclei, the solid cores of comets, because they're geologically fascinating. A comet's nucleus is typically a few kilometers across, though it can be smaller or larger. The nucleus is the only part of the comet that's truly solid. The coma and tail are just gas and dust. We've only directly observed a handful of comet nuclei. The Rosetta spacecraft provided detailed images of Comet 67P's nucleus, revealing it to be a contact binary with a highly irregular shape. The Deep Impact mission provided images of Comet Tempel 1's nucleus, showing craters and boulders. From these observations, we know that comet nuclei are highly irregular. They're not spherical. They have complex shapes with lobes, depressions, and protrusions. Porous. They're not solid blocks of ice. They have voids and cavities, possibly from sublimation or impact processes. Compositionally varied, different regions have different compositions. Some areas are richer in certain types of ice. Others have more dust. Geologically active, jets of gas erupt from the surface. Dust is continuously ejected. The surface is changing. Relatively dark. Comet nuclei are surprisingly dark. Comet 67P's nucleus has an albedo, reflectivity, of only about 0.04, meaning it reflects only 4% of the sunlight that hits it. It's darker than coal. This is probably because organic material and dust cover the surface, darkening it. The darkness is significant because it means comets don't reflect much light even when illuminated by the sun. This makes them inherently faint objects. When comets appear bright to us, it's usually because of the light scattered by dust and gas in the coma and tail, not from the nucleus itself. Now, let me tell you about something called the Great Comet classification, because some comets are historically more significant than others. A great comet is typically defined as a comet that becomes bright enough to be visible in daylight or that achieves a magnitude brighter than zero, a standard astronomical measure of brightness. Great comets appear infrequently, maybe once or twice per century. The last great comet before the modern era was Comet Ikea-Seki in 1965. The comet became so bright it was visible in daylight. Its tail stretched across much of the sky. It was one of the most spectacular comets in recorded history. Before that, Comet C/1882 R1, the Great Comet of 1882, was a great comet visible in daylight. Hale-Bopp in 1997 was approaching great comet status. It was bright and widely visible, though not quite reaching daylight visibility. Neowise in 2020 was the brightest comet since Hale-Bopp and was visible to the naked eye, though not a great comet by the traditional definition. The unpredictability of comet brightness makes it difficult to predict which comets will become great comets. A comet that's predicted to be faint might suddenly brighten. A comet expected to be bright might fade unexpectedly. Let me tell you about comet composition and what different compounds tell us. When a comet approaches the sun and begins to sublime, different ices evaporate at different temperatures. Water ice sublimates relatively easily. Methane and ammonia ice sublime more readily still. Carbon dioxide ice, dry ice, sublimates very easily. By observing which molecules are ejected from a comet at different distances from the sun, astronomers can determine the composition and structure of the comet's nucleus. Some comets are rich in water. Others have substantial amounts of methane or ammonia. Some have high organic content. The ratios of different molecules vary from comet to comet. Interestingly, comets have different D/H ratios. The ratio of deuterium, a heavy isotope of hydrogen, to normal hydrogen. This ratio varies depending on where in the solar system the comet formed. Comets from the Oort cloud generally have higher D/H ratios than comets from the Kuiper belt. This suggests the two populations formed in different regions of the early solar system, the Oort cloud from farther out, the Kuiper belt from closer in. By measuring D/H ratios in comets and comparing them to Earth's D/H ratio, scientists have tried to determine how much of Earth's water came from comets. The answer is complicated. Some evidence suggests comets delivered significant water to Earth. Other evidence suggests most of Earth's water came from asteroids. Now let me talk about extinct comets and how periodic comets eventually die. A periodic comet doesn't last forever. Each time it passes near the sun, it loses material through sublimation. Eventually, after many orbits, the comet runs out of volatile ice. The nucleus becomes inert. The comet is now extinct. An extinct comet might still orbit the sun, but it no longer displays the characteristic coma and tail. From a distance, it looks like an asteroid. Some asteroids are thought to be extinct comets, cometary nuclei, that have lost all their ice and now appear as ordinary asteroids. One example is Comet Encke, a periodic comet with a very short period, 3.3 years. Encke has been observed for over 200 years. Its orbital period has been gradually shortening, which suggests it's losing mass due to outgassing. Eventually, after thousands more orbits, Encke will become completely inert. Another example is Comet Pons-Winnetka, which has a period of 6.4 years. This comet has become much fainter over the past century, suggesting it's running out of volatile material. Some comets last longer than others. Halley's Comet has been returning for thousands of years and is still displaying a substantial coma and tail. But eventually, even Halley's will run out of ice and become extinct. Let me tell you about some upcoming comets that might be visible in the coming years. Comet 6P/D'Arrest is a periodic comet with a period of 6.5 years. It was last seen in 2018 and is due to return around 2024 to 2025. It's typically faint and requires binoculars or a small telescope to see. Comet 7P/Ponce-Winnecke is a periodic comet that should be observable in the coming years with optical aid. It's currently fading but might brighten slightly at certain points in its orbit. Comet C/2023 A3 Tsuchinshan Atlas appeared in late 2024 and was visible to the naked eye in some regions. It's one of the brightest comets in recent years. Comet 12P/Ponce-Brooks is expected to return to the inner solar system in 2024. It's a periodic comet with a period of about 71 years. Last apparition was in 1953. This comet is known for occasional outbursts, so its brightness is unpredictable. It might be visible with binoculars or a small telescope. None of these comets are expected to be as bright as Halley's Comet or Hale-Bopp, but for observers with binoculars or small telescopes, they offer opportunities to see comets in the coming years. Now let me tell you about something called non-gravitational forces, because they make comet orbits unpredictable. We normally calculate orbits using gravity. A comet orbits the Sun due to the Sun's gravitational pull. Its orbit can be mathematically predicted, but comets experience forces beyond gravity. The outgassing we discussed, the ejection of material as ice sublimates, creates a reaction force. This reaction force is unpredictable because it depends on which parts of the comet sublime, which depends on the comet's rotation and the detailed thermal structure of the nucleus. These non-gravitational forces can significantly alter a comet's orbit. A comet's predicted return date might be off by days or weeks because of non-gravitational forces we couldn't predict. This is why comet observations are so important. Even after a comet has appeared multiple times, its orbit remains uncertain. Each new observation refines our knowledge of the comet's trajectory and helps us predict future appearances more accurately. Let me tell you about the Oort cloud's origin, because it's a story of cosmic violence and orbital chaos. The Oort cloud wasn't always where it is. Billions of years ago, the early solar system was different. When the solar system first formed, the region where planets now orbit was filled with planetesimals, small bodies of rock and ice. These planetesimals were initially in relatively circular orbits in the same plane, but as the giant planets formed and migrated, they stirred up the planetesimals. Gravitational encounters between planetesimals and planets scattered the planetesimals into chaotic orbits. Some planetesimals were ejected completely from the solar system. Others were thrown into highly elliptical orbits. The ones with the most highly elliptical orbits, the ones that extended far from the Sun, ended up in the region we now call the Oort cloud. Over billions of years, these scattered planetesimals settled into the Oort cloud's spherical shell. They orbit the Sun, but at enormous distances and from random directions. The Oort cloud is, in a sense, the graveyard of the early solar system. It contains the remnants of planetary formation scattered far from the Sun. And occasionally, a passing star nudges one of these distant bodies, sending it falling towards the inner solar system. When it arrives, it becomes a comet. So every bright comet we see is a visitor from the violent chaos of the early solar system, arriving after billions of years in the cold outer darkness. Now let me tell you about the connection between comets and the origin of life on Earth. Life on Earth requires certain chemical elements and compounds: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. It requires water. It requires organic molecules, the building blocks of proteins, nucleic acids, and lipids. Earth formed as a terrestrial planet in the hot inner solar system. In the early stages, Earth was too hot for complex organic molecules to survive. The chemical building blocks of life couldn't accumulate on the young Earth's surface. But then, after Earth had cooled, after a few 100 million years, the late heavy bombardment began. Comets and asteroids from the outer solar system collided with Earth in enormous numbers. These impacts brought water. They brought organic compounds. They brought the chemical raw materials for life. Some scientists propose that life's origin depends critically on cometry and asteroidal delivery. The organic compounds that led to life didn't originate on Earth. They came from space. This hypothesis is called panspermia, and while it's not universally accepted, there's evidence supporting it. Meteorites contain amino acids. Comets contain organic compounds. Experiments have shown that organic compounds can form abiotically in space through chemical processes. If comets did deliver the chemical precursors of life to Earth, then we literally owe our existence to comets. Every living thing on Earth, every plant, every animal, every microorganism owes its ancestry to materials delivered by comets billions of years ago. Let me tell you about amateur comet discovery, because it's a field where amateurs can make significant contributions. Professional astronomers use automated surveys and telescopes to discover comets. But amateurs, people with binoculars or small telescopes, still discover comets regularly. To discover a comet, you need to observe the sky carefully, know where comets typically appear, and recognize the fuzzy appearance of a comet as opposed to a galaxy or nebula, which look similar. Several famous comets were discovered by amateurs. Comet Shoemaker-Levy 9 was discovered by David Levy and the Shoemakers using a 0.4-meter telescope. Comet Hyakutake was discovered by Yuji Hyakutake, a Japanese amateur astronomer. Comet Hale-Bopp was discovered independently by Alan Hale and Thomas Bopp, both amateur astronomers. When an amateur discovers a comet, they report it to the International Astronomical Union's Central Bureau for Astronomical Telegrams. If the discovery is confirmed by other observers, the comet receives a designation, and the discoverer's name is attached to it permanently. This is one of the last fields of astronomy where amateurs can make discoveries that bear their names. Most other areas of astronomy require professional equipment and expertise. But comet discovery remains accessible to dedicated amateurs with modest equipment. Now let me tell you about tidal disruption of comets, because it's a spectacular end for some comets. We discussed Comet Shoemaker-Levy 9 fragmenting due to Jupiter's tidal forces. But tidal disruption can happen with any large body, planets, moons, even the sun. When a comet passes close to a massive body, the gravitational pull is stronger on the side closer to the massive body than on the far side. This differential gravitational force is called a tidal force. If the tidal force is strong enough, it can overcome the comet's self-gravity and tear it apart. Comet Shoemaker-Levy 9 was particularly susceptible to tidal disruption because it was already weakened. It had previously passed close to Jupiter and was held together only. 1992 close encounter with Jupiter shredded it into about 20 fragments. Other comets have been disrupted by the sun. A comet passing very close to the sun might be tidally disrupted if it gets close enough. The resulting fragments might then follow separate orbits. Tidal disruption is a way for comets to end, not by sublimating away, but by being torn apart by gravitational forces. Let me tell you about comet detection methods and how astronomers find comets today. Visual observation. Amateur astronomers using binoculars or telescopes scan the sky manually, looking for fuzzy objects that might be comets. This method is less common now, but still used. Photographic surveys. Automated telescopes take repeated photographs of the sky. Computer software compares successive images to identify moving objects. Many comets are discovered this way. Digital imaging. Modern surveys use digital cameras and automated detection algorithms. Surveys like Pan-STARRS, ZTF, Zwicky Transient Facility, and others systematically scan the sky and detect moving objects. Spectroscopy. Once a potential comet is detected, spectroscopy confirms it's a comet by identifying the spectral signatures of water, carbon dioxide, and other gases specific to comets. Astrometry. Precise measurements of the object's position allow astronomers to calculate its orbit and predict future positions. The detection methods have become increasingly automated and sophisticated. Most newly discovered comets are found by digital surveys rather than visual observation. Now let me tell you about something called the Great Comet of Naming Convention, because it reflects historical astronomy. Before the modern nomenclature system was established, bright comets were often referred to as the Great Comet of Year. The most famous examples are the Great Comet of 1811, the Great Comet of 1882, and the Great Comet of 1910, which was actually Halley's Comet. These names reflect the cultural impact of these comets. They were so bright and so widely observed that they became defining events of their years. People born in those years might remember the comet for their entire lives. The term Great Comet is no longer officially used, but it persists in historical context. Modern bright comets like Hale-Bopp are sometimes informally called great comets by the general public, even though they don't meet the technical definition. Let me tell you about comet mythology and ancient observations, because they reveal how humans have understood comets across cultures. In many ancient cultures, comets were considered omens, but the specific meaning varied. In Chinese astronomy, comets were documented systematically for thousands of years. Chinese astronomers recognized that comets were recurring phenomena. Detailed records from as early as 500 BCE describe comet positions, brightness, and tail directions. Some of these ancient records allow modern astronomers to identify which periodic comets were observed centuries or millennia ago. In European medieval times, comets were generally seen as bad omens. The appearance of a comet might be interpreted as predicting the death of a king, the outbreak of war, or the arrival of plague. This belief persisted into the Renaissance. In Islamic astronomy, comets were studied as natural phenomena. Persian and Arab astronomers made detailed observations. The 13th century astronomer Nasir al-Din al-Tusi described comet observations and attempted to classify them. In Aztec cultures, comets were associated with the god Quetzalcoatl and were interpreted as signs of significant events. Across virtually all the ancient cultures, comets held special significance. They were unusual, unexpected events in the sky. Their sudden appearance seemed to demand explanation. They were interpreted as messages from the gods, or as harbingers of change. With the development of modern astronomy, the mystical interpretation of comets faded, but they retained their cultural significance as objects of wonder and beauty. Now let me tell you about something called the comet graveyard hypothesis. Some astronomers have proposed that there's a region of space beyond the Oort cloud where cometary bodies accumulate, where they eventually end up after being scattered by stars and gradually falling inward. This comet graveyard would be a region of extreme density, a halo of comet-like bodies extending potentially to many thousands of astronomical units from the Sun. This hypothesis is speculative and unproven, but it highlights an important point. The solar system is larger and more complex than our simple models suggest. There might be populations of small bodies we haven't detected and don't fully understand. Let me tell you about historical comet brightness records and what they tell us. Ancient Chinese astronomical records provide the longest continuous record of comet observations. Some comets recorded in Chinese documents from 2,000 years ago can be identified as the same periodic comets observed in modern times. For example, Halley's Comet appears in Chinese records going back to at least 240 BCE. The records describe its brightness, position in the sky, and tail appearance. By comparing ancient brightness estimates with modern observations, astronomers can learn about how comet brightness has changed over centuries. Some periodic comets appear to have been brighter in ancient times and have faded over the centuries. This is consistent with the theory that periodic comets gradually lose volatile material and become less active over time. Other comets show no obvious long-term trend in brightness, suggesting they've reached some kind of equilibrium where the amount of material lost per orbit equals the amount replenished by thermal processing of the nucleus. Now let me tell you about impact risk from comets. Because it's a real but relatively small threat, comets are much less common than asteroids, so the probability of Earth being struck by a comet is lower than the probability of an asteroid impact. However, comets can be more dangerous than asteroids of equivalent size because comets travel faster. Comets approaching from the Oort cloud travel at very high velocities relative to the Sun and Earth. An impact from a high-velocity comet would release more energy than an impact from a slower-moving asteroid. Comets are less predictable. Because of non-gravitational forces and outgassing, comet trajectories are hard to predict. A comet could appear suddenly without much warning. Comets can be large. Some comets have very large nuclei. A multi-kilometer comet impact could be catastrophic. However, statistically, the risk from comets is lower than the risk from asteroids simply because there are far fewer comets passing through the inner solar system. Scientists monitor both asteroids and comets for potential impact threats. So far, no large comet has been detected on a collision course with Earth in the foreseeable future. Let me tell you about comet spectroscopy and what it reveals about composition. When light from the Sun passes through a comet's coma, molecules in the coma absorb and emit light at specific wavelengths. By analyzing the spectrum of light from a comet, astronomers can identify which molecules are present. Common molecules detected in comet spectra include H2O, water, identified by absorption bands in the ultraviolet C, O2, carbon dioxide, identified by specific emission lines CO, carbon monoxide, common in many comets, CN, cyanide radical, produces a blue color in comets, C2, diatomic carbon, produces a green color N, H2, amidogen radical, identified by specific spectral features. The relative abundances of these molecules vary from comet to comet. Some comets are CO-rich, meaning they have high levels of carbon monoxide. Others are more typical, with water as the dominant volatile. These compositional differences are thought to reflect where the comet formed in the early solar system. CO-rich comets might have formed in different regions than water-rich comets. By studying comet spectra, astronomers learn about the chemical diversity of cometary bodies and the conditions in different regions of the ancient solar system. Now let me tell you about sun-grazing comets, because they're spectacular and doomed. A sun-grazing comet is a comet that passes extremely close to the sun, sometimes within just a few thousand kilometers of the solar surface. These comets pass through the sun's corona, the hot outer atmosphere. Sun-grazing comets are extremely rare and extremely bright. As they approach the sun, they heat up dramatically. Ice sublimates explosively. The coma becomes immense. The tail stretches across the sky. But sun-grazing comets are also doomed. The intense heat near the sun can vaporize the nucleus completely. Many sun-grazing comets don't survive their encounter with the sun. They evaporate entirely, leaving nothing behind. The most famous sun-grazing comet was Comet Ikeya-Seki in 1965. This comet passed within about 500,000 kilometers of the sun's surface. The sun's radius is about 700,000 kilometers, so the comet came very close. The comet became extraordinarily bright, visible in daylight. Its tail stretched across much of the sky. After the encounter, the comet faded rapidly as it had lost most of its material to sublimation. Sun-grazing comets often belong to a group called the Kreutz group, which are thought to be fragments of a single large comet that broke apart centuries ago. The Kreutz sun-grazers follow similar orbits and return to the sun's vicinity on regular schedules. Let me tell you about comet nuclei sizes and how they relate to the Great Comet phenomenon. Comet nuclei typically range from a few hundred meters to perhaps 50 kilometers in diameter. Most observed comets have nuclei in the range of 1 to 10 kilometers. A comet's brightness is not determined solely by nucleus size. A small comet with a large coma and tail can appear brighter than a larger comet with a smaller coma. The coma and tail's size depend on the comet's activity level, how much material is being sublimated. A comet's activity depends on distance from the sun, closer equals more sublimation. Surface composition, some areas sublime more readily than others. Nucleus rotation affects which areas face the sun. Nucleus temperature affects sublimation rate. Nucleus structure, more porous nuclei sublime more readily. So two comets of similar size might appear very different in brightness if their activity levels differ. This is why comet brightness is so unpredictable. We can estimate a comet's activity based on its past behavior, but unexpected changes can occur. Now let me tell you about the possibility of panspermia via comets, that life itself might have come from comets. The panspermia hypothesis, in its strongest form, suggests that life originated elsewhere in the universe and was transported to Earth by comets or meteorites. In a weaker form, panspermia just suggests that organic compounds and water necessary for life originated in space and were delivered to Earth by comets and meteorites. Evidence supporting a role for comets. Comets contain water. All comets are icy bodies containing abundant water, the solvent for life. Comets contain organic compounds, amino acids, nucleotide bases, and other biological molecules have been detected in meteorites of cometary origin and inferred to be present in comets. Comets delivered water to Earth. Isotopic ratios in Earth's water are different from the Sun's, suggesting Earth's water came from elsewhere, possibly from comets. Comets may have been more abundant in the early solar system. Models suggest there were more comets impacting Earth in the first few 100 million years than exist today. However, the evidence is debated. D/H ratios in Earth's water don't perfectly match comet D/H ratios, suggesting that either comets delivered only some of Earth's water, or the D/H ratios have changed over time. Organic compounds in meteorites could have formed on asteroids rather than comets. The origin of life remains one of science's deepest mysteries. Even if comets delivered water and organic compounds, the question of how non-living chemistry becomes living biology remains unanswered. Most scientists accept that comets and asteroids delivered significant amounts of water and organic material to early Earth. Whether this delivery was necessary for life to originate, or whether life could have originated without it, remains an open question. Upcoming comets to watch. Comet 13, P/Olbers, periodic comet, period approximately 72 years, last appeared in 1956, expected to return around 2024 to 2025, may be visible with binoculars. Comet 103, P/Hartley, periodic comet, period approximately 6.5 years, relatively faint but occasionally brighten unexpectedly. Comet C/2024, G3, Atlas, long-period comet discovered in 2024. Its brightness is uncertain but being monitored. The brightness of comets is notoriously difficult to predict. A comet expected to be faint might surprise us with unexpected brightening. A comet predicted to be visible to the naked eye might fade below visual magnitude limits. The best approach is to keep monitoring comet predictions from organizations like the International Astronomical Union and comet-specific websites that track all known comets. Now let me tell you about comet tails and light pressure, because it's a counterintuitive physics. Solar radiation carries momentum. When photons from the sun hit dust particles in a comet's tail, they transfer momentum to those particles. This creates a radiation pressure force pushing the particles away from the sun. For large dust particles, this radiation pressure is relatively weak. The particles are still pushed, but the effect is small. For very small dust particles and gas molecules, radiation pressure can be significant. Gas molecules in the ion tail are pushed strongly by the solar wind and radiation pressure, creating a tail that points almost exactly away from the sun. Very small dust particles are pushed by radiation pressure, but they're also affected by gravity and solar wind. The result is that the dust tail curves slightly. It doesn't point exactly away from the sun, but lags behind the comet's motion. This creates the characteristic appearance of comet tails, the ion tail pointing straight away from the sun, the dust tail curving backward. In extreme cases, radiation pressure can overcome gravity entirely. A comet very close to the sun can lose dust particles so rapidly via radiation pressure that the dust tail becomes very faint or even invisible. Let me tell you about comet radio observations, because they reveal things that visible light observations don't. Radio astronomers observe comets by detecting radio emission from molecules in the coma. When molecules are excited by ultraviolet radiation from the sun, they can emit radio waves at specific frequencies. Different molecules emit at different frequencies. By observing radio emissions, astronomers can identify molecules. Different molecules have characteristic radio emission frequencies. Measure outgassing rates. The intensity of radio emission correlates with the amount of material being ejected. Detect molecules hidden from visible observation. Some molecules don't produce visible light, but do emit radio waves. Radio observations complement visible and infrared observations, providing a more complete picture of comet composition and activity. Now let me tell you about comet orbital dynamics and the three-body problem. Comet orbits are calculated using gravitational physics. In the simplest case, we treat the comet as a test particle orbiting the sun, and we calculate the orbit using the sun's gravity alone. But in reality, the planet's gravity affects comet orbits. As a comet approaches the inner solar system, it passes near planets, usually Jupiter. The planet's gravity alters the comet's trajectory. For most comets, planetary perturbations are small, but for some comets, especially those passing close to Jupiter, planetary gravity can significantly change the orbit. This is the three-body problem, calculating the orbit of a body under the gravitational influence of two or more massive bodies. The three-body problem has no general analytical solution. It can only be solved numerically. Astronomers use sophisticated numerical integration techniques to calculate comet orbits, accounting for perturbations from all the planets. This allows them to predict where a comet will be with reasonable accuracy. However, non-gravitational forces, outgassing, introduce additional uncertainties that can't be perfectly predicted. Let me tell you about something called cometesimals and the early solar system. Cometesimals are thought to be the smallest building blocks of the early solar system, tiny, icy, rocky bodies that later aggregated into larger comets and planetesimals. Cometesimals would have been meter-sized or smaller bodies composed of ice and dust. In the cold, outer solar system, countless cometesimals orbited the Sun. As the solar system evolved, gravitational interactions caused cometesimals to collide and aggregate. Over time, small cometesimals combined into larger bodies, the proto-comets and planetesimals that eventually became the source of today's comets. The cometesimals themselves are no longer observable. They've all been incorporated into larger bodies. But they represent a crucial stage in the solar system's formation and structure. Understanding cometesimals helps us understand how the solar system organized itself and where modern comets came from. Now let me tell you about the emotional and cultural impact of comets on human civilization. Comets have always captured human imagination. They're rare, unexpected, and beautiful. Their appearance inspires awe. In ancient times, comets inspired fear. They were interpreted as omens of disaster. Their sudden appearance and equally sudden disappearance seemed to demand supernatural explanation. In the Middle Ages, comets inspired both fear and scientific curiosity. Religious authorities might interpret comets as signs of God's will, while scientists and natural philosophers attempted to understand them through observation and calculation. In the modern era, comets inspire wonder and scientific interest. When bright comets appear, like Hale-Bopp in 1997 or Neowise in 2020, millions of people observe them. They inspire art, music, poetry, and literature. Comet Hale-Bopp inspired a religious cult that believed the comet was accompanied by a spacecraft that would transport the cult members to a higher existence. 39 people died in a mass suicide hoping to board this spacecraft. This tragic example shows how comets can inspire extreme reactions. But more commonly, comets inspire wonder and a sense of connection to the cosmos. When you observe a comet, you're observing something that originated in the distant outer solar system. You're seeing a remnant of the early solar system. You're connected to billions of years of cosmic history. That's why comets matter culturally as well as scientifically. Let me tell you about comet jets and outbursts in detail. As we discussed, comets develop jets, narrow streams of gas and dust ejected from the nucleus. These jets are not uniformly distributed around the nucleus. They occur in specific regions where sublimation is most intense. The location of jets depends on nucleus rotation. As the nucleus rotates, different areas face the sun. Areas facing the sun heat up and sublime more readily. Surface composition. Some regions have different ice compositions or different dust-ice ratios, causing uneven sublimation. Topography. Depressions or shadowed areas sublime differently than exposed areas. Jets can be quite narrow and intense. Observations of Comet 67P by the Rosetta spacecraft showed narrow jets extending from specific sites on the nucleus. These jets are significant because they create non-gravitational forces. The reaction force from ejected material alters the comet's orbit unpredictably. Create asymmetry. The coma becomes asymmetrical due to uneven jet activity. Cause outburst. Sudden changes in jet activity can cause sudden brightness increases. Now let me tell you about comet fragmentation mechanisms in detail. Comets fragment through several mechanisms. Rotational instability. As a comet sublimates, it loses mass. This causes its rotation to speed up, like an ice skater spinning faster when pulling in their arms. Eventually, the rotation becomes so fast that centrifugal force exceeds the nucleus's self-gravity, and material is ejected or entire fragments break off. Thermal stress. The side of the nucleus facing the sun heats up while the shadowed side remains cold. This creates internal temperature gradients that cause stress and fracturing. Tidal forces. When a comet passes near a massive body, tidal forces can exceed the nucleus's self-gravity and tear it apart. Impact. A collision with an asteroid could fragment a comet. Outgassing pressure. Internal pressure from sublimating ice can rupture the surface and eject material. Different comets fragment through different mechanisms. Some comets fragment gradually over multiple orbits. Others fragment catastrophically in a single event. Let me tell you about the Rosetta mission in detail, because it's one of the most important comet missions ever. The European Space Agency's Rosetta mission was launched in 2004 and arrived at Comet 67P/Churyumov-Gerasimenko in 2014. It orbited the comet until 2016. Not all sublimated material escapes the comet immediately. Some molecules sublime beneath the surface and must migrate through the porous nucleus to escape into space. The outgassing efficiency describes what fraction of sublimated material actually escapes versus what fraction recondenses inside the nucleus. A comet with high outgassing efficiency loses material rapidly and develops a large coma. A comet with low outgassing efficiency retains material internally and develops a smaller coma. Outgassing efficiency depends on nucleus porosity. A more porous nucleus allows better gas escape. Nucleus temperature profile affects where sublimation occurs and where recondensation might happen. Gas molecular weight. Lighter molecules escape more readily. Nucleus composition affects sublimation temperature and recondensation probability. By measuring a comet's coma size and outgassing rate, astronomers can infer properties of the nucleus that might not be directly observable. Let me tell you about comet spectral classification schemes that astronomers use. Comets can be classified by their spectral characteristics. Water-dominated comets show strong water emission lines and weak CO/CO2 lines. CO-rich comets show anomalously strong carbon monoxide emission relative to water. CN normal comets show typical cyanide radical emission relative to water. CN deficient comets show unusually weak cyanide emissions. Depleted comets show weak emission in all species, indicating low activity. These spectral classifications correlate with orbital characteristics. Long-period comets tend to be more active and water-rich. Periodic comets tend to be more depleted and CO-rich, having lost volatile material over many orbits. Some comets show unusual spectra that don't fit standard classifications. These exotic comets might have unusual compositions or unusual activity patterns. Spectral classification helps astronomers understand comet diversity and evolution. Now let me tell you about comet nucleus rotation periods and what determines them. Comet nuclei rotate, typically with periods ranging from a few hours to several. Most meteorites originate from asteroids, but some meteorites originate from comets. When Earth passes through a comet's debris trail, cometary meteoroids enter the atmosphere and produce meteors, meteor showers. Occasionally, larger pieces survive and fall as meteorites. Cometary meteorites are rare because comet material is fragile. Comets are loosely bound, porous ice and dust. Material from comets is more likely to be destroyed by atmospheric friction than material from solid asteroids. However, some meteorites are identified as cometary in origin based on their composition and mineralogy. These cometary meteorites provide direct samples of comet material. Now let me tell you about comet activity cycles and seasonal variations. A comet's activity level varies as it orbits the Sun. Far from the Sun, a comet is essentially dormant. The nucleus is frozen and inert. As the comet approaches the Sun, pre-perihelion activity. When the comet is still millions of kilometers from the Sun, the surface begins to warm. Ice begins to sublime. The coma forms and grows. Activity increases. Maximum activity typically occurs near perihelion, closest approach to the Sun, when the nucleus is most heavily illuminated and heated. Post-perihelion activity. After perihelion, the comet begins moving away from the Sun. It continues to outgaze, but at decreasing rates. Activity gradually declines. Far from the Sun, when the comet is beyond a certain distance, sublimation essentially stops. The coma fades. The comet becomes dormant again. The exact timing and intensity of activity varies from comet to comet depending on nucleus composition and structure. Some comets show unexpected activity variations, outbursts, or sudden fading that don't follow the expected thermal pattern. Let me tell you about the discovery of the Oort cloud itself, because it's an interesting historical story. The Oort cloud wasn't directly observed. It was inferred theoretically. In the 1950s, Dutch astronomer Jan Oort analyzed the orbital characteristics of long-period comets. He noticed that long-period comets seem to come from random directions in the sky, not preferentially from any particular direction. He also noticed that the long-period comets had orbital eccentricities very close to 1.0, a parabolic or nearly parabolic orbit. This suggested they were making their first or early passage through the inner solar system from a very distant source. Oort calculated that if comets came from a spherical shell surrounding the solar system at a distance of roughly 100,000 astronomical units, this would explain the observed orbital characteristics. He proposed that this shell, which came to be called the Oort cloud, contains billions of comets, all orbiting the Sun at vast distances. This was a remarkable theoretical prediction. The Oort cloud has never been directly observed. It's too far away and too dark. But the prediction remains consistent with all observational evidence. Nearly all long-period comets show orbital characteristics consistent with coming from an Oort cloud population. Now let me tell you about comet interception missions and future plans. Several space agencies have considered or planned missions to intercept comets beyond just orbital observations. Deep Impact 2005 was the first deliberate comet impact, as we discussed. OSIRIS-REx and Hayabusa 2 are primarily asteroid missions, but their techniques are applicable to comets as well. Rendezvous, sample collection, return to Earth. Proposed future missions include direct nucleus sampling, landing on a comet nucleus and extracting samples for return to Earth. Comet deflection, deliberately altering a comet's trajectory to study how its structure responds. Multiple comet encounters, a spacecraft visiting several comets in sequence. The challenge with comet missions is that comets are fragile and unpredictable. The outgassing can create hazards for spacecraft. The low gravity means samples don't stay put. The irregular shape complicates landing and sample extraction. Nevertheless, scientists are eager for more direct comet exploration, as comets hold secrets about the solar system's origins and possibly about life's origins. Let me tell you about comet tail disconnection events, because they're dramatic and poorly understood. Occasionally, a comet's tail suddenly disconnects from the nucleus. The tail detaches and drifts away into space while a new tail forms. Tail disconnection events are thought to be caused by sudden changes in the solar wind or magnetic field configuration. The solar wind's magnetic field can become twisted or compressed. When this happens, it can sever the connection between the comet's ion tail and the nucleus. The disconnected tail continues drifting away, but the comet remains unharmed. Within hours or days, a new tail begins forming. Tail disconnection events have been observed in several comets and are captured in photographs. They're dramatic illustrations of the dynamic interaction between comets and the solar wind. The exact mechanisms causing tail disconnection are still not fully understood, but they're of great interest to plasma physicists studying solar wind-comet interactions.